T, 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 we got T. Oh, T, 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 let's go. Yo, what up? Welcome back to Goblin Goes to Harvard. We're on PredictionX part 2 out of 3. We're on PredictionX Lost Without Longitude. My brain is actually awake, which is nice. It's a nice change. Might be time to clean my kettle. My tea tastes funny. Somebody probably snuck some arsenic in it. Okay. Are you guys ready? Are you ready for this? Bum 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 bum. Yo, what up? Yo, what? Alright. Start the course. What is navigation? I do have notes to take on the side, but I don't know if my note taking is just bad, but I didn't like it was useful for the test, but like so I'm still gonna take notes, but they didn't seem very useful for like you guys to see. Well, whatever. Guide page. What is navigation? Latitude and longitude. Navigation as prediction. Longitude, prize, and GPS. Help, I'm lost. Yo! Finding your way at sea. Assessments. Tools of the navigator. Videos. And then it stops. Alright. Overview of the course for help navigating. For an overview of the course or for help navigating the content at any time, visit the guide page in the slide menu above. Description. Oh, look, there's an AI that's going to tell me what the questions are. We're not going to use that. We don't use stuff like that. Not in this place. Not here. Can you use a sextant? I've never used a sextant, so presumably not. I'm not one of those people who assumes I can do things that I've never done before. You know there are people that do that? I've never played tennis in my life. Yeah, I could definitely score a point against Serena Williams. Fucking Christ. To navigate is to move from one location to another by way of an intended course. Alright. And we agree with that definition? I think that definition is fine. By this definition, humans have been navigating for millennia, and as cultures developed different techniques and tools for ascertaining location and discerning route, navigation grew into a practice, an art, and a science. Navigational prowess has long been tied to commercial, economic, and military success. Being able to predict when and where one will reach a distant destination is more than just a key to empire building. It is a matter of life and death. I mean, I use the term navigation when I'm talking about social scenarios, right? When I'm talking about, like, how do you navigate a crisis, like a social crisis, right? How do you navigate your relationships? You plot a course and figure out how you're going to get from point A to point B, right? Watching some of Pan Bondi's testimony. Holy shit, it was a train wreck. Yeah, that sounds about right. Our understanding of space and time and the ways we move through them are necessarily influenced by the society we inhabit, the way in which it's organized, and the technologies it produces and on which it relies. The GPS in 21st century smartphones uses satellite signals to ascertain terrestrial locations and overlay them on highly accurate maps, and it is so reliable that people today almost never think about how challenging navigation really is. They find it hard to believe that developing an accurate way to measure longitude was once a scientific challenge as important as curing cancer is today. Well, yeah, I mean, it's nice to be able to know where you're going. And how to get there. Traditional navigation. In early history, it was not taken for granted, or even believed in many cases, that measurement of the natural world was possible, or that mathematical calculations could yield a reliable predictive system, and portable, accurate navigational instruments were not available. As a result, navigational systems were not as mathematical as they usually are today. Instead, ancient mariners relied on natural phenomena and landmarks, like the wind direction at particular locations or shoreline features, to chart courses and determine location. Many navigators today still incorporate these traditional techniques, and we highly recommend John Huth's book, The Lost Art of Finding Our Way, to learn more about navigational techniques that do not rely on complicated instruments. I will give you guys this so you guys can check it out if you are interested. Yeah. It's if there's something that you take for... You remember we were talking the other day about Vic Mignogna being like, oh, people take things for granted, and he picked, like, the dumbest shit? Yeah, navigation is probably, like, if there's something that people fucking take for granted, it's fucking Google Maps. Even just having a paper map at your, like, at a convenience store. Like, that's something I think people take for granted. How does a sextant work on a flat Earth? Yeah. All of this is gonna be applicable to being like, fuck flat Earthers. Next. A mere 3,000. Oh, wow, neither of those were correct. 300 years ago, some of the world's greatest minds and imperial powers were locked in a race to discover an accurate way to determine location and thereby navigate accurately at sea. I guess, do you guys think that you could make that comparison to, like, the space race? Like the Cold War? Where it's like, we're trying to do this thing faster than other countries? It's like the three big ones I can think of is, like, France, Spain, and England, right? Trying to all, like, vying for naval control. And, like, the Northwest Passage and stuff like that. In other sections of this course, we explain why navigation, the prediction of one's path through space-time, was and is so critical to our study. But here, we sort out some critical terminology and a bit of astronomy, because astronomy is in everything. Bro, astronomy is in everything. In case you're not already an expert. Is Landon here? Do we have an astronomy expert here? No, I don't think we do. Spurs. I don't think kids today could show you the cardinal directions while standing outside. There's not... I guess that depends on where you live. Right? Like... At least when I was a kid, most kids could figure it out. It might take them a second, but they would figure it out because, sun rising and setting is like the... Now, if you make it at nighttime, make them do it at night, then that's hard mode. That's hard mode, boys. Schedule your live stream to members only. No, why would I do that? Go away. Go away, YouTube. You're drunk. 3 centuries ago, as now, location was specified on the Earth's surface using latitude and longitude. The equator, defined by a plane perpendicular to the Earth's spin axis, serves as a natural 0 for latitude, but longitude has no analogous natural 0 point. The Earth's spin on its axis makes the sun and stars appear to move in the sky in repeating patterns that makes it easy to determine north-south position latitude, but hard to find east-west location longitude. In the late 1800s, more than a century after the general problem of finding longitude at sea, because there's nothing, right? If they're generally using landmarks and stuff like that, and you're in the middle of the fucking ocean, weeks away from shore. I made an assumption that kids go outside. Had been solved by a clockmaker and astronomers. The world's most technologically and scientifically advanced nations were still trying to map exactly where in the world they were relative to each other. The ease and ubiquity of modern technologies make such challenges seem absurd. But what if your smartphone's battery died or your GPS stopped working while you were out at sea? What if you were truly lost? How might you navigate then? You have to have a chance, you'd either need to rely on cues from nature or you need to rely on more traditional means of finding latitude and longitude, the meanings of which we explain using the videos below. I'm going to click on this link. I want to see where it goes. Oh, it goes to a video. Does it go to one of the videos that are down here? Oh, no. Okay, so we should watch these. All right. So determining north-south position latitude.
John, when you're doing this, do you do multiple measurements? Or sometimes, you know, I mean, if you're on a boat.
Yeah, what you can do when you get at the altitude of a star, normally if you think of the way it gets projected onto the Earth, it's going to be a huge circle. That's just, you know, where there's multiple places. And if you have two stars, you'll get two circles. But the modern, so-called modern, I guess 1875 onward, trick was you make an estimate of your latitude and your longitude, and then rather, if you think about a circle, if you get very close to the edge of the circle, it becomes a line. And so one star will give you a line of position that you must lie on, and then if you take the altitude of a second star at some angle, you'll get a second line of position, and then you use the intersection of those two lines of position to figure out where you are in terms of latitude and longitude. So practically, that's how you do it. That's the modern way. Back a long time ago, people would watch the sun rise, get to its highest point in the sky, and then set, and they would use the highest point in the sky to assess a latitude. And if you had a clock, you could use that timing to assess a longitude, but it's less precise because of the motion of the vessel itself. The vessel is moving as you're taking all these sightings, and so it's not quite easy.
Catching when the sun is at its culmination, you know, you're watching it sort of as it gets asymptotic there, it's slowing down, and so you might take a number of quick readings because you're not sure if you've gotten the highest point. But that, and then it's more, introduces more error. And
you know what this sounds like? Trigonometry. So what if your GPS stopped working? What does this go to? Is it another video? Yeah, it is. It goes in the square hole.
I'd like to play back this conversation for the crews of the Holland America ships, because the true story is that I went on a cruise. I think I told you this when my house started leaking last February, and I went to the bridge because I told them that I was sort of, you know, trying to study this subject, and the captain said, "Oh, that sounds interesting. Why don't you come visit me?" So his navigators gave me a lovely tour of the bridge, and I said, "This is great that you have all these electronic systems and your GPS, and what's your backup system? Can I see all your, you know, stuff?" And they said, "Oh, we have 2 GPS systems." And then they proceeded to like find the closets that had various sextants and compasses and a nautical almanac from 2 years ago, and yeah, so it was a little scary.
That makes sense to me. Like, it makes sense to me to have 2 GPSs because they're kind of not a big deal to have. So it makes sense to me that you would have 2 of them and have like a backup one. So that doesn't seem scary to me. That seems like it makes complete sense. Like, a lot of the times you don't keep your backup tools in arm's reach because, you know, they're not the fire extinguisher. Blah, 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 videos below. Heroes in the history of latitude and longitude. Thanes? Whatever. Head librarian of Alexandria in the 3rd century BC is perhaps best known for measuring the circumference of the Earth using little more than shadows and basic geometry. However, he is also credited with inventing geography. Wow. This dude invented geography? That's kind of huge. His 3-volume book, Geographica, mapped the entire known world, and introduced the geographic coordinate system of parallels and meridians still in use today. Using this grid-like overlay of what we now call latitude and longitude, people were, for the first time, able to predict measured distances between two far-off locations and, more importantly, considered their local position in reference to a global one. Hipparchus was a Greek astronomer in the 2nd century BC who is credited with compiling a catalog of the positions of the last 850 stars, improving the measurements of the motions and distances of the sun and moon, and improving and or inventing several astronomical instruments. Hipparchus applied these celestial insights to the geography of Eratosthenes, arguing that latitude could only accurately be ascertained through stellar measurements as opposed to solar altitude, and positioning that longitude could be derived from simultaneous observations of a lunar eclipse by wedding the old science of astronomy to the new geography. Hipparchus greatly increased the accuracy of latitude and longitude and paved the way for navigation we know today. Man, that's crazy. Hipparchus?
The measurement of latitude and longitude uses what is called a geographic coordinate system. The Earth's spin offers a natural orientation for these measurements, which uses the equator and the two poles as reference points to form a grid covering the entire globe.
I feel like we read this already.
The poles are the points where Earth's axis of rotation meets its surface, and the equator encircles the Earth, perpendicular to the spin axis, midway between the poles. Rings parallel to the equator show constant latitude, and rings going through the north and south poles show constant longitude. These north-south rings are called meridians. Longitude measures position east or west of an arbitrary zero meridian. Latitude measures how far one is north or south of the equator. The equator offers a natural zero point for latitude, but longitude has no natural zero point. Today, we use Greenwich, England, also known as the prime meridian. Lacking a reference point, longitude is much harder to determine than latitude and requires utilization of the Earth's motion as time. Since a day is one spin around the axis, or 360 degrees in 24 hours, the Earth spins at a rate of 15 degrees of longitude per hour.
The Flurfs hate him because he invented geography? I wonder if we're ever going to, like, invent or find better, more accurate ways. Like, a GPS is pretty accurate, so I just don't know if we'd need to. But I mean, I guess you have interstellar measurements. Like, you don't necessarily have a latitude and longitude that way, but we don't necessarily need it. So, like, for Star Trek, right? Like, what does the Star Trek navigation system actually do? That I don't know. I think it's interesting. A lot of human invention comes from need,
The
right?
measurement of time on Earth is integrally tied to place and place to time. Viewed from a perspective above the North Pole, the Earth appears like a giant 24-hour clock turning counterclockwise. One rotation is 1 day, or 360 degrees in 24 hours, and so the world turns at a rate of 15 degrees per hour.
What was that thing that definitely didn't happen because of the holy energies? I think of them as holy energies because the energies are full of holes.
This relationship between space...
That's right, it was Bob. This is Bob Nodell, right?
And time has been used by navigators for centuries to determine where and when they are in their journeys around the world.
Yeah, I mean, time using the Earth's rotation to help measure the Earth is and like figure out where you are makes sense. It makes sense to me. To navigate is to predict. Okay. Okay. Is it? Go on.
I would like to ask John why we should think of navigation as prediction.
Well, I can give you 2 examples.
Like, well, what a chill dude.
One is just walking through the park, let's say. So as you walk through the park, you have some mental map of what the surroundings look like, where there's a fountain, where there's a tall tree, something like that. And you would predict that if you're walking a certain distance, you're going to see a fountain. So you're always comparing your mental prediction to what you're seeing in terms of landmarks. Now, let's say you walk some distance and the fountain didn't appear, then you would start to panic and you'd be lost. So in a way, you're mentally constructing this path that you're taking through time and space and predicting what you might be seeing. So that's the simplest example. For navigation at sea, when, say, we have a sextant and a chronometer and a set of tables, you might know where you are at a certain point from a fix using the stars, and then you proceed at a certain speed and heading, compass heading, which is direction, and then in a process that we call dead reckoning, which is basically...
Never underestimate the necessity and the power of a good navigator at sea.
Using that information, you predict where you are, and then you pull out
The
the
worth.
sextant at an opportune moment and do it again and verify whether you are there, and in fact sometimes you aren't, and then you attribute a current pushing you along to that. So it's this succession of predicting where you are, reducing that circle of uncertainty. That circle of uncertainty grows, and then when you identify something unambiguous, it shrinks again.
You're really ideally predicting where you're trying to go, right? I mean, you're trying to predict where you're going to be. That's the sort of futuristic part of it, right?
So you have an ultimate goal, but you have a set of waypoints in mind, and you're constantly trying to verify those waypoints as a way of assuring yourself that you're on the right path.
This is one of those things that I think like kids start doing intuitively. Unless you're one of those people who has like, what is it called? When you like, you basically, you turn around and you completely lose all sense of what direction you're facing. There's like, it's like a thing. It's like a whole ass thing where somebody can like basically blink, like close their eyes for half of a second, rub their head, open their eyes and not know where they are anymore in relation to anything else. It's like, I don't remember what it's called, but it's crazy. To navigate is to predict where and when you will be at future points if you take particular route from where you are. Yeah, okay. To predict movement through space and time, one needs to know position, direction, and speed. The smaller the uncertainty in these quantities, the more accurate one can predict one's path. I think this is applicable to like just life. That's just life advice. You have to know where you are to know how to get to where you want to go effectively. So, like, if you don't know where you are in life, or know, like, what's bothering you, or know where you want to go, how can you possibly navigate anywhere? You're just arbitrarily going in random directions. And, you know, part of life is, like, trial and error, right? Like, which is fine. Like, there's nothing wrong with that. But, like, if you want to, I don't know, fix your relationship, then you kind of need to understand where you are in the relationship in the first place. And then probably knowing how you got there can help you avoid the same pitfalls between point A and point B. Disoriented? Well, they get disoriented, yeah, but that's not the word I'm looking for. The word I'm looking for is like a technical term. It's a medical term. I don't remember, though. I forgot to put the predictor up, or I forgot to put the give me the certificate thing up. Oh well, it's okay. The ultimate form of object permanence. Uncertainty. Physicists are particularly fond of the term uncertainty, which is ironically an expression of a degree of certainty ascribed to a measurement. Uncertainty is often described in terms of standard deviation or margin of error. To take a real-world example, imagine you're given a metric ruler to a large group of high school students and ask them all to measure the length of the same 8.5 by 11 inch piece of paper to the nearest millimeter. The mean value the students measure should be 11 inches expressed in millimeters, 279 millimeters, but a graph of the frequency of all results would show a bell-shaped curve with some width, sometimes called a dispersion, that represents the uncertainty in the measurements. That width will go up and down as the number of students in our thought experiment goes up, or as their eyesight improves, or as they care with which they make measurement, or the care with which they make measurements improves. But it will never be zero. The finite width, which is the standard deviation for the margin, if errors are random, is the uncertainty of the measurements of the paper's length. The uncertainty in any kind of measurement is always a combination of instruments, like a ruler, accuracy of the users, the students, care in making the measurements. The uncertainty in a prediction is determined by both the uncertainty of input measurements as well as the accuracy or validity of the predictive system to which they are input. So, how good are you? Can you consistently guess like 60 seconds? Like if you were just to sit quietly and then like put an X on a piece of paper, like set a timer and put an X on a piece of paper, how close are you to 60 seconds every time? There's a great but longish video from Adam Savage about measurement error and the philosophy of measuring things. Oh, that's cool. Don't deny reality, like and share the screen instead. Thanks, bye, I've finished and remember for 12 months at the Iron Goblin level. Hail, and hail reality. Let's go! Position. Position is about knowing where you are relative to another place, or relative to a reference system like a latitude and longitude. Yeah, that makes sense. Everything is relative. Distance is defined by the separation of the two positions. In some units, for example kilometers, standardized units for measuring distance have evolved greatly in terms of accuracy and replicability. From the hired pacers of Alexander the Great to the laser light wavelengths determined meter, today, but the appreciation of the importance of standardized distance units is at least 5,000 years old. Yeah, right? Like, because everybody, like, how big is a foot? I don't know, how big is your foot? It's different than my foot. Oh, it just goes to Wikipedia about meters. That's neat. Direction. On land, humans' natural propensity is to aim for particular landmarks that can be seen from a distance. The direction of one's course is adjusted using the ability to aim. So, like, interestingly enough, like, I don't know if this is everywhere. In Canada, a lot of the times when we're measuring, like, the distance to travel, we're measuring it in time. We're not actually measuring it in kilometers. Or, like, how far it actually is. So, like, very rarely do I hear people say, like, oh, it's like 2 blocks that way. People will be like, oh, it's like 5 minutes that way if you're walking. Right? So, like, people will be like, oh, it's like 5 minutes that way. It's like, oh, it's about 45 minutes away. And so, like, the 45 minutes is assumed you're taking the highway at about 100 kilometers an hour. Right? Because there's only one road in Canada. The big-ass fucking highway. So, like, people measure in time rather than actual distance. Like, if I had to be like, oh, how far is it from, like, I don't know, Kitchener to Toronto, I'd probably tell you, I don't know, it's about an hour and a half, 45 minutes with no traffic. And then we put the traffic in, too. So it's like, we measure things in time more often than we measure in distance. Which is kind of interesting. I don't know if it's like that everywhere, though. I don't know if other places do things differently. And like that also depends like on who you're talking to, because sometimes people will be like, oh, it's about this long if you're taking the bus, or it's about this long if you're taking a bike, or it's about this long if you're taking the train, right? Due to consistent traffic, distances in Los Angeles are measured, are time-based as well. That's interesting. I wonder if there's a correlation between the amount of traffic and the time, like the use of time as a measurement instead, because then if there's traffic, the distance doesn't really matter because you're gonna get slowed down, right? So the question people are really asking when they're saying like, hey, how far is it somewhere? They're not actually asking about the distance. They're actually asking about how long it's going to take them to get there, right? Interesting. Never given time as the unit of measurement for distance? Really? Really? Never? Not even once? That can't be. That can't be true. No. Come on. Really? That's amazing. Anyway, direction. On land, humans' natural propensity is to aim for particular landmarks that can be seen from a distance. The direction of one's course is adjusted using this ability to aim. Direction is specified mathematically as an angle relative to the fiducial line. Did I pronounce that right? Fiducial? I don't know what this is. Maybe I do know what this is and I just can't remember. Sometimes I know words that I've never read before.
Fiducial.
Fiducial. Based on or relating to faith or trust, relating to characteristic of a legal trust, fiduciary. Ah, that is a word I recognize. Regarding or employed as a standard of reference as in surveying. So that's the one we're using. Standard of reference. Angle relative to the fiducial line. So, for example, a human walking towards a tree will try to keep her direction at 0 degrees relative to a line extending from her position to the trees. I feel like this could be really easily explained in Minecraft. You know what I mean? Was that Brett's voice? Whoa! Surprise, Brett Keane. Ba-la-la-la. Oh man, that would be a really funny meme. That would be a really funny meme. I never interact with Brett Keane though. Like he doesn't even like come by tertiarily. Like I don't come across him in the wild in any real way. I feel like you could do this in Minecraft and it would be really easy to like lay it out for somebody. When humans need to navigate over long distances or at sea though, their built-in landmark-based system fails. So, for millennia, I mean, that makes sense. We're not really exactly meant to be in the ocean like that. So, for millennia, navigators have overcome the limitations of their innate systems using cardinal directions, north, south, east, west, to orient themselves with respect to an imaginary grid tied to the Earth's surface and thus to faraway locations. Due to geography and many roads not being grid-based, going around mountains and ranges, etc., distances in California on the 100-mile scale are hours of travel rather than miles. Yeah, that's a good point. Like the terrain, the topography, tapioca? That would matter. That makes a lot of sense. How far is it? An hour down the road. An hour, but it's just down the road. Yes, an hour with traffic. Oh, hi. Debunk the funk. Oh, that's fun. Cardinal directions. The segmentation of the horizon into 4 sections, call them winds, corners, or cardinal directions, appear to be a cultural universal. Really? I guess that makes sense. Especially when you add astronomy into it, because astronomy is universal as well. Anthropologists suggest that the prevalence of this 4-way split is derived from the human body and our perception of space composed of a front, back, and 2 sides. Sure. As we watch a faraway event like a rising sun, we project this orientation out as far as the eye can see, all the way to the horizon. In this way, scholars hypothesize that such a human experience catalyzed the abstract sectioning of the sky dome. Oh no, not the sky dome. There's no, you can't use words like that. The flat earthers are gonna come. The sky dome into 4. The repetition of celestial events like eastern rising and western setting, circumpolar stars, and zenith positions provided and still provides consistent reference points for orientation, which were used in conjunction with landmarks to find and keep direction. For instance, if you can see the Big Dipper and Cassiopeia, you'll notice a star between them that doesn't seem to move over the course of the night. Instead, all the other stars in the sky seem to revolve around it like a giant backwards clock. This star is Polaris, the North Star. Now imagine the shortest arc possible stretching from Polaris down the horizon. Polaris doesn't move much, and so this point where the arc connects to the horizon wouldn't move either. This would be very beneficial because we could now draw a circle around the entire horizon, measuring out 360 degrees from this fixed 0 point. We could give this point a name like north and derive a system of directions using it as reference. The use of celestial motions was reliable enough to orient the corners of the Great Pyramid of Giza to within an average deviation of 0 degrees 1 foot 47 inches from the intercardinal directions. So, like, the thing with that is, like, if you make a small measurement error, it compounds over time. So if you don't keep checking it, you'll get further and further away from your intended destination. But I mean, it makes sense that you would, like, the star being the star, right? Like, this fucker doesn't move. Especially when everything else is moving. Firmament is an interesting phenomenon, to be sure, though people who believe it are even more so. Today, the magnetic compass has become a ubiquitous instrument. I've been doing really well reading today, and I think I deserve a treat. I've been doing really good. Today, the magnetic compass... Oh, I guess we click on this. I feel like this is going to go to Wikipedia. No, no. It's a video. Oh, no, it's a different... What? Do I need to read this here, or I'm going to... Oh, I guess I'll just read it now. Compasses are the simplest... At their simplest are magnets suspended in such a way that their north pole points towards Earth's north pole. Larger compasses were made of a single piece of lodestone hung on a thin rope. Smaller ones are magnetized iron or steel, either balanced on a small point or floated in oil or water. Compasses are most reliable near the Earth's equator. Earth's magnetic field is not perfectly aligned with the planet. The geomagnetic north is located about 10 degrees from the physical North Pole. Local differences in the strength and direction of the magnetic field can also cause issues with navigation. So you kind of have to just, you know, compensate for that, I guess. Today, the magnetic compass has become ubiquitous. Oh. English. Instrument for finding north and measuring angles relative to north. The compass uses a magnetized piece of metal. Is this going to take me to the same fucking thing I just read? No. Okay. A magnetized piece of metal which spins freely to align itself with the Earth's magnetic field. Stop the stupidity for 2 cents. For the words. Yeah, words and shit. Listen, I'm doing really well today, okay? I'm doing good. I never fucking read this well, all right? Reading out loud is way harder than you think. Especially for an audience. Like, they catch everything. Fox, socks, box, knocks. I should start doing that again as a warm-up. I haven't done it in a long time. Lodestones are naturally magnetized rocks, specifically a mineral known as magnetite. Insert Pokemon joke here. Lodestones have two uses in navigation. First, they may be used as compasses in and of themselves. If they are hung from a rope, they will naturally turn until the north pole of the magnetite points towards the Earth's north pole. Second is the more common. They can be used to magnetize iron or steel needles by rubbing a piece of ferrous metal with a lodestone. One can magnetize the smaller metal, which is useful for replacing compass needles when they rust or lose their magnetism. The magnetic property of lodestone was known by the 6th century BCE. Its use as a compass dates to the 11th century CE in China and about 1300 in Europe. Wow. Man, bro, China was ahead of the curve on a lot of this shit, apparently. That's pretty cool. I hate reading to people. Why? Is it because reading out loud is hard? Rodent. Why are you bullying me? What does this even say? And unification has been superioristic. Did I get it right? The magnetic pole of Earth at present is very near the truth. Oh, I forgot to put the music on. Oh man, guys, I'm sorry. I forgot. I thought about it before going live, and then I forgot about it by the time I hit the fucking button, man. Oh, hold on. Okay, we're gonna turn the volume down on that. It still seems a little loud. How's that? Is that good? That should be okay, right? Is that fine? You guys let me know and I'll make adjustments. Cool and rainy tomato soup and warm toast day. Yeah, I was thinking about making soup today too, actually. I think soup's a good idea. I'm gonna make cream of broccoli soup with some onions and garlic. Public domain Baroque music would go hard. You have a link to that? I put this one on. I'll share it with you, the one that I put on. So that way you guys can use it. This one is supposed to be copyright free, and so far I have not had any problems with it for being copyright free. So here you go. Where was I? The magnetic pole of the Earth at present is very near the true North Pole, where one end of the Earth's spin axis crosses its surface. So a compass gives a good approximation of true north. Without a compass, navigators can and did rely on the sun, stars, and moon in addition to weather and wave patterns to discern references at sea. These directions were compared to maps, stories, songs, and other representations of the world and helped navigators know where to go so long as they knew where they were on their map. Speed. Speed is the distance traveled per unit time. To measure speed accurately, one needs to measure both distance and time accurately using standard units for each. I think I remember the equation for velocity, but I don't remember velocity is speed in the equation, right? Because you can have ramping velocity as well, right? It's v equals t divided by d, like time divided by distance. Is that what it is? If I'm remembering correctly, I'm trying to go back to like grade 10 math right now, like grade 10 science. It wasn't even in my math class that they taught this. This was in my my generalized science test class. Is it velocity equals time divided by distance? I don't remember. To measure speed accurately, blah 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 blah. Fingers, fists, feet, and arms have. Oh, it's. Oh, I was close. It's distance divided by time, not the other way around. Yeah, velocity is speeded in a specific direction. Right. There's no deviation on it. The biggest innovation in maritime navigation was a mechanical clock that would work on a rolling ship. That is pretty cool. They did mention that, like, clockworkers were one of the biggest contributors to accurately distance time equals speed. Yeah, distance divided by time. I was close. I had time and distance backwards. I was so close. You gotta give me some credit for that. It's been like over a decade. 2 decades. I'm only 17. Well, how old am I? I don't know. Whatever. Fingers, fists, feet, and arms have all been used as units of measurement to describe longer and longer distances, but no such human-related analog was relevant to travel on the open ocean. That's true. How many washing machines? With the widespread use of latitude and longitude grids in map making, the nautical mile was adopted for long distances. While nautical miles work nicely on charts, suffice to say that in spite of their elegant original specifications as 1 arc minute of latitude, a sixth of a degree, they are very hard to use directly in measuring the speed of a moving ship. It takes too long to go a nautical mile. One can easily lose track of one's position and the time over that long a distance. Right, so it's like I was saying earlier, when you get one measurement, you have to keep making that measurement or you're gonna go off course. Miles per hour. Get out of here. At the typical speeds humans travel, even on a fast ship, it is much easier to use distances much shorter than a nautical mile while measuring speed. For example, innovative simple devices like chip logs let sailors measure over a short and measurable length of time how much rope pays out off the stern of the ship as it moves through the water. The length of the rope divided by the length of the time gives the ship time gives the ship's speed. Okay, yeah, that makes sense. Of speed's numerator and denominator, distance and time, it's historically been... How are you using these terms in this course? Okay, like, I know what a numerator and a denominator is, right? Like, I don't know if I'd be able to give you a functional definition, but, like, I know what it is. But, like, how are you gonna go from the last one, which was, like, fucking tea leaves, and now we're talking about fucking numerators and denominators of measuring distance, time, and speed? Like, I feel like we may have taken a little bit of a jump to the left, you know what I mean? Like, the other one I feel like you could literally just pick up and do, and you wouldn't really have to look up any words. Oh, you wouldn't have to look up any terms. Right? You could just do it. This one does not feel like that. Like, I feel like if you didn't, like, if you were to just pick this one up, on average, you'd have a lot more people having to look up what a numerator and denominator are. Imperial systems be like Bingus Borch per whistle wonk. Yes. Of speed's numerator and denominator, distance and time, it's historically been harder to measure time very accurately. Over the centuries, many technologies were developed to try and capture time. Sundials and astrolabes are at least 2,000 years old and were used on ships into the 16th century. Sundials use the shadow of the sun to point out time on a face similar to a modern clock face. As the sun moves across the sky, different numbers are touched by the shadow of the gnomon pointer, and this gives the local time or the solar time, and cities at different longitudes would record different times on their sundials. Sundials might be carefully built and aligned. A sundial created for the use at one latitude will give exact times at other latitudes and times of the year. Many sundials even have 2 or more hour lines carved into them to indicate times in, for example, the summer and the winter. And then there's sunlight recorders, armillary spheres. Similar devices were used at 1500 BCE. They were still in common use in navigation until the 18th century. Sundials are primarily decorative today. They are pretty. I should get one. I should make my own. Astrolabes. Takes Harvard course, complains about words she knows. I didn't mean to complain. Alright, you didn't have to call me out like that. Alright, like, come on. Astrolabes had a multitude of uses, determining the local time, finding the altitude of celestial bodies, finding the direction to Mecca, surveying, and triangulation. Many later models were also inscribed for use as rulers and protractors, or with star charts. As some of the most sophisticated and beautiful tools for navigation and astrologers, astrolabes were also a symbol of intelligence and sophistication. Many astrolabes have been discovered that had serious errors, such that a real practitioner would immediately have noted them as fakes. These were probably sold to rich individuals who wanted to seem sophisticated to their guests. What? Oh, people wouldn't do that. That's not something bad. Come on. You're born to lead, not to read. For that, read the title. Okay, fair. Alright, no, fair. Okay, you got me. High five. Oh, that makes me happy. Wonderful. I love that. That's so good. I love what we have. The mariner's astrolabe was a much simpler instrument designed for the pitching decks of ships rather than use on land. About 200 BCE into the 17th century. Oh, I want one of these. That'd be so cool. It'd be really cool if I could learn how to use it. Look at that thing. Oh, there's videos down here. Oh my god, have we been missing out on videos and I just didn't fucking notice? Oops. I just didn't scroll down far enough? Uh-oh. Well.
One way to find angle of the sun or the North Star was to use an astrolabe.
This is an astrolabe. It's sort of like a planisphere that you might buy at a planetarium, for example. It's a map of the stars. I can identify certain ones like Deneb and Vega, and Sirius, and so on. So this would show the motion of the sky as it goes around, and against the inner plate. Let me take it apart so you can see what I mean. This is the sky chart with the constellations. No, not really, but the star names are written there in Arabic. And then this base plate shows where the horizon would be for a particular latitude. Now, if you want it in a different latitude, well, you have to pick the plate that will be useful, and you get a choice because it's both sides.
How far do they go? What range of latitudes?
They will have Mecca and Medina on, and then because it was made in India, it will have a number of Indian cities. that can be used. And as a matter of fact, there's a gazetteer in here that lists the cities and tells you what the latitude of them is. And the other thing, it tells you what is the direction to Mecca.
The astrolabe has Arab roots or no? Is that
The
true?
astrolabe goes back to the 4th century. It has Greek roots. It evolves through the Muslim world and Arabic world. And then in the Middle Ages, it gets back over to the Latin West through Spain and Greece and expands from there. This is a model of a planispheric astrolabe. They has all these star pointers here. But if you're on a ship, you don't need those star pointers. It's an expensive addition. Plus, there's a big problem. The wind is going to blow against this, then it's going to push it. So by 1500, a new form of astrolabe is invented known as the mariner's astrolabe, and it's like a big cast bronze wheel.
Big
This
thick
boat,
boy.
Big areas for the wind to blow through. Very heavy. And all it has is, doesn't have any of this stuff. Doesn't have any of these other charts here. It just has a divided circle here of degrees and a sighting rule known as the alidade. So it's like a stripped down planispheric astrolabe.
That's interesting. I mean, it makes sense because why would you spend a bunch of money on information you don't need, right?
I think people collect objects like that today with often not really knowing how to use them.
Well, that's true because there's a lot of fake astrolabes. If you
Oh, God. No, I was in Marrakech and I was hoping to purchase an astrolabe, and all the stuff that these guys showed me were junk. I mean, it was and expensive junk at that, too.
John's a funny guy.
Very disappointing. So.
Yeah, I actually have to write a person who just contacted me with an astrolabe they got in Morocco that they were told was, from the such and such century, and it had been in this one family since 1920, and this whole thing. And I have to write him back. I've been pausing on it because I have to tell him. But he wants to know how to use it, and he's a scholar. He's actually an astronomer, and I have to tell him it's jewelry. It was made yesterday, and all the parts don't make any sense.
Oh, that's sad. That's sad.
So you would cite
Bro got ripped
with
off.
this what's known as an alidade.
What are the little sighting vanes then? Do you not?
this,
Yeah.
well, that's so that you can get the altitude of a star. You can then figure out what your latitude is, and it might help you.
Decide which of the plates to use.
And you can work out the time of day and so on. So it will act as a watch or a timekeeper, but it also is the whole idea of holding the universe in your hands.
I don't know how I feel about that, but sure. Institute of Navigation's Navigation Museum has a page on the Mariner's astrolabe. Well, if you're interested, check this out. More detail on how astrolabes work from howstuffworks.com. Howstuffworks.com. And description from the astrolabe translated from text by Cerberus Sabocht, Circa 650. Brother! Whoa. Okay, very cool. That's really neat. If you want to learn how this fucking thing works. Cool. An in-person demonstration for my TED Talk. How long is it? Oh, it's only 9 minutes. Yeah, we watch these.
Technology progresses And as it advances, many of us assume that these advances make us more intelligent, make us smarter, and more connected to the world. And what I'd like to argue is that that's not necessarily the case, as progress is simply a word for change. And with change, you gain something, but you also lose something. And to really illustrate this point, what I'd like to do...
I'm sorry, is this man positing the the laws of equivalent exchange? Is that what I'm hearing right now? The laws of, that, like, when you gain something, you lose something of equivalent value?
Is to show you how technology has dealt with a very simple, a very common, an everyday question, and that question is this. What time is it? What time is it? If you glance at your iPhone, it's so simple to tell the time. But I'd like to ask you, how would you tell the time if you didn't have an iPhone? How would you...
So when I went on vacation, we go every year for a week or two, depending, right? I used to be very, when I was younger, I don't do it very much anymore, but I used to be able to tell exactly what time it was on that beach. Because it's like, it's about 2, it's about noon, it's about how hungry am I? Is it lunchtime yet? So yeah, if you're in a clear spot and you're regularly in the same place and you just pay attention, you'll be able to tell what time it is at certain times of the year, just based on just practice.
Tell the time, say, 600 years ago. How would you do it? Well, the way you would do it is by using a device that's called an astrolabe. So an astrolabe is relatively unknown in today's world, but at the time, in the 13th century, it was the gadget of the day. It was the world's first popular computer, and it was a device that, in fact, is a model of the sky. So the different parts of the astrolabe in this particular type, the rete corresponds to the position of the stars, the plate corresponds to a coordinate system, and the mater has some scales and puts it all together. If you were an educated child, you would know how to not only use the astrolabe, you would also know how to make an astrolabe. And we know this because the first treatise on the astrolabe...
Oh, that's cool. That you know how to make one? Oh, I want to make one. Oh, man.
The first technical manual in the English language was written by Geoffrey Chaucer. Yes, that Geoffrey Chaucer in 1391 to his little Lewis, his 11-year-old son.
Like the character from A Knight's Tale? That guy? It's called a lance. Hello.
And in this book, little Lewis would know the big idea. And the central idea that makes this computer work is this thing called stereographic projection. And basically the concept is, how do you represent the three-dimensional image of the night sky that's...
Bro, little Lewis at 11 years old knew how to fucking tell that the Earth was fucking a globe.
...surrounds us onto a flat, portable two-dimensional surface. The idea is actually relatively simple. Imagine that the Earth is at the center of the universe, and surrounding it is the sky projected onto a sphere. Each point on the surface of the sphere is mapped through the bottom pole onto a flat surface where it's then recorded. So the North Star corresponds to the center of the device. The ecliptic, which is the path of the sun, moon, and planets, correspond to an offset circle. The bright stars correspond to little daggers on the rete, and the altitude corresponds to the plate system. Now, the real genius of the astrolabe is not just the projection. The real genius is that it brings together two coordinate systems so they fit perfectly. There's
the astrological
and
and
the planets on the movable rete, and then there's their location on the sky as seen from a certain latitude on the back plate. Okay? So how would you use this, this device?
You should be able to make this with cardboard. Like or Bristol board. You theoretically should be able to do it with like Bristol board.
Well, let me first back up for a moment.
Paper and one of those push pins.
This is an astrolabe. Pretty impressive, isn't it? And so this astrolabe is on loan from us from the Oxford School of Museum of History, and you can see the different components. This is the mater, the scales on the back. This is the rete, okay, do you see that? That's the movable part of the sky. And in the back you can see like a spider web pattern.
Part of this seems like something I would get out of a fucking Cracker Jack box, and it would be on a ring, you know what I mean? And it fucking made out of like garbage.
And that spiderweb pattern corresponds to the local coordinates in the sky. This is a rule device, and on the back are some other devices, measuring tools, and scales to be able to make some calculations. Okay? You know, I've always wanted one of these. For my thesis, I actually built one of these out of paper.
I told you could build it out of paper. Yeah, fucking. I fucking knew it. Fucking nailed it. Fucking paper mache, dude. Hell yeah.
This is a replica from a 15th century device.
I thought this guy was gonna have jokes and say that one was a replica of the one he made out of paper for his thesis. Oh well. Alas.
For my thesis, I actually built one of these out of paper. This is a replica from a 15th century device, and it's worth probably about 3 MacBook Pros, but a real one would cost about as much as my house, and the house next to it, and actually every house on the block, on both sides of the street, maybe a school thrown in, and some, a church. They're just incredibly expensive. But let me show you how to work this device.
You think Elon Musk has one?
So let's
I bet Elon Musk has a fake one because he's stupid and would buy the wrong thing.
go to step 1. First thing that you do is you select a star in the night sky if you're telling time at night. So tonight, if it's clear, you'll be able to see the summer triangle, and there's a bright star called Deneb. So let's select Deneb. Second is you measure the altitude of Deneb. So step 2, I hold the device up, and then I sight its altitude there so I can see it clearly now. And then I measure its altitude. So it's about 26 degrees. You can't see it from over there. Step 3
Oh, that's
is
so cool.
identify the star on the front of the
It's
device.
trigonometry.
There, I can tell. Step 4 is I then move the sky, so the altitude of the star corresponds to the scale on the back. Okay, so when that happens, everything lines up. I have here a model of the sky that corresponds to the real sky. Okay, so it is, in a sense, holding a model of the universe in my hand.
Now, I have another question. After a long enough period of time, these astrolabes won't be accurate anymore because, like, the sky moved, right? The Earth moved its position from, like, right? Am I right about that? Like, so, like, I mean, it might not be by a lot, but there should be, like, a degree of change. Now, it might not be enough to make these measurements, like, invalid or not, like, or wholly incorrect. But, like, that, am I right about that?
My hands. And then finally, I take a rule and move the rule to a date line, which then tells me the time here. Right? So that's how the device is used. So I know what you're thinking. That's a lot of work, isn't it? Isn't it a ton of work to be able to tell the time as you glance at your iPod to just check out the time?
To be fair, it really does change our ability to tell where things are when we have satellites. Like, once you're in space and you're able to look down at the whole thing, it makes measuring and finding places on that thing a lot easier than when you're smack dab in the middle of buttfuck nowhere.
But there's a difference between the two, because with your iPod you can tell, or your iPhone, you can tell exactly what the time is with precision. The way little Lewis would tell the time is by a picture of the sky. He would know where things would fit in the sky. He would not only know what time it was, he would also know where the sun would rise and how it would move across the sky. He would know what time the sun would rise and what time it would set. And he would know that for essentially every celestial object in the heavens. So in computer graphics and computer user interface design, there is a term called affordances. So affordances are the qualities of an object that allow us to perform an action with it. And what the astrolabe does is it affords us to connect to the night sky, to look up to the night sky and be much more, to see the visible and the invisible together. So that's just one use. It's incredible.
That's really cool.
There's probably 350, 400 uses. In fact, there's a text that has over 1,000 uses of this first computer. On the back, there's scales and measurements for terrestrial navigation. You can survey with it. The city of Baghdad was surveyed with it. It could be used for calculating mathematical equations of all different types, and it would take a full university course to illustrate it. Astrolabes have an incredible history. They're over 2,000 years old. The concept of stereographic projection originated in 330 BC, and the astrolabes come in many different sizes and shapes and forms. There's portable ones, there's large display ones, and I think what's common to all astrolabes is that they're beautiful works of art. There's a quality of craftsmanship and precision that is just astonishing and remarkable. Astrolabes, like every technology, do evolve over time. So the earliest reeds, for example, were very simple and primitive, and advancing reeds became cultural emblems. This is one from Oxford.
Oh yeah, like obviously, like once you've got it down, you start adding to it, right? It's like playing cards. Right? You have the first set of cards invented, and then they start getting more elaborate from there, and they have different usages and games and imagery and all kinds of stuff.
And I find this one really extraordinary because the reed pattern is completely symmetrical, and it accurately maps a completely asymmetrical or random sky. How cool is that? It's just amazing. So would little Lewis have an astrolabe? Probably not one made of brass. He would have one made out of wood or paper. And the vast majority of this first computer was a portable device that you could keep in the back of your pocket.
Could you imagine having one of those, like a pocket watch size? Oh man, that's so cool.
So what does the astrolabe inspire? Well, I think the first thing is that it reminds us just how resourceful people were, our forebears were, years and years ago. It's just an incredible device. Every technology advances. Every technology is transformed and moved by others. And what we gain with the new technologies, of course, is precision and accuracy. But what we lose, I think, is an accurate, a felt sense of the sky, a sense of context. Knowing the sky, knowing...
Yeah, I would agree with that. I think you lose. I think when you just look at your phone for the time, you're not really thinking about how you figured out what time it was because you didn't do any of the work. It's all done by a computer in the back.
Your relationship with the sky is the center of the real answer to knowing what time it is. So I think the astrolabes are...
Getting a little bit in the philosophy, I guess, but like the philosophy of self a little bit, but sure.
They're just remarkable devices. And so what can we learn from these devices? Well, primarily that there's a subtle knowledge that we can connect with the world, and astrolabes return us to this subtle sense of how things all fit together and also how we connect to.
I mean, that's really cool. I don't know why it cut off at the very end there, but that's really cool. That's really neat. I want to make one. And now I have to go back and find out if there are like fucking videos for all these because I didn't notice. So I didn't scroll down far enough. Oh yeah, there's videos that I fucking missed. All right, I'm gonna take a break first, then we'll go back and watch those other videos. But now I want to make an astrolabe. So if you guys want me to make an astrolabe, you fucking let me know, and we'll see if we can figure it out. I have to buy. Hey, you know those things that like those little cases that you have to buy in like high school that have like a protractor and the fucking triangle and the compass and the fucking measuring one. Like there's the one with the 2 points on it that all the kids stabbed each other with. You know what I'm talking about? Yeah, they never taught us how to use like half of those things. I only ever learned how to use the fucking protractor, and I only ever learned how to make a circle with the compass one. They didn't really tell us or teach us how to use any of these tools. They just required that we had them. So that was kind of wacky. Discord DMs? Okay, we'll look at that first. What did you... Oh, Etsy listing. Oh boy. What's this gonna be? Oh man, it's a tiny little pocket watch size one for $61. Is it fake? Is it accurate? How do you know? I bet it's not accurate. I bet it's garbage. But that's so cool. Oh, I want one. All right. I'll be back. We're taking a break. We'll be back in a couple minutes. Hello, I'm back. I figured I'd give us like the 20 seconds because I think what that guy was describing was like a sense of grounding and a sense of context. Like, when he was talking about the sense of context, it's like a little bit of grounding, sort of like you exist in this place. I got an apple. My mom has an apple tree, so she gave me a shitload of apples, so. Is an apple good for breakfast? This is the first thing I've eaten today. Are apples good for you for breakfast? I don't know. I don't know if there's too much sugar in them or the right kind of brain food. You tell me. I'm not good at nutrition. I don't know these things. Educate me. I'm stupid. Alright. We have other videos to watch. We gotta go backwards, so this one's a lodestone.
Now with a compass, you need always a lodestone, a magnet, because when you went on a ship, you often carried multiple compasses because they were too important. If one, broke, you wanted others, but you always wanted to make sure that it was magnetized, the compass needle. So you always carried a big rock, a natural, like you see here, which was a naturally magnetic piece of ferrite ore.
I do like that humans deciding how to navigate things over distances is to trust a big rock. That is like a very like monkey brain, fucking unga bunga ook ook motherfucker. Like that's very like such a human thing. Can you imagine aliens? Aliens being like, what are they doing? Oh, they're carrying around a giant rock. Why are they carrying that rock around? It tells them where to go. What do you mean it tells them where to go?
Known as magnetite, and this common name was a lodestone from the lodestar, the star that the North Star, so because it would magnetize the compass needles, which would point north.
Rock. Oh, you took a look at the how it works. Oh man, that's so cool. That's so cool. We're saving this for later. This is its own thing. Now, its astrolabes are now their own thing. Alright. Lodestones and needles from Ocean Navigator, an article on the history of magnetic navigation. So, if you're interested in that. There we go. Yeah, okay, that was the right one. Navigation before Netscape from History Magazine. That doesn't work. Some of these links don't work. Wikipedia's page. I'm not going to share Wikipedia's page. It's fine. The unarmed lodestone. I feel like I've seen this kind of thing before. I think I've been to a museum that has these, or had these. We rub the rock and it makes magic metal to show the way. That is a compass. That is what a compass is. I've convinced Harvard to let you into their school as an official student, the first Goblin student ever. Oh, well, thank you. I appreciate it. I didn't realize you had that kind of power, Borgenporia. Damn. Damn. That's cool. All right. So that was lodestone. I will try to put these links in the description afterward, I guess. Get out of here. Okay, there we go. Compasses.
Let's look at a couple of mariners' compasses up close. So this one is how they would be on a ship. This one is made and sold in Boston in the mid-19th century, so like 1840, 1860s. And this one is sold by Frederick W. Lincoln. I'm going to take it apart a little to show you. So first of all, what the card looks like. This box is known as the binnacle. It's a protective box to keep it safe on the ship.
You have to protect it from the heavenly energies.
With anything like this, where it's a life and death thing is depending on it, you are regularly calibrating and checking your instruments. Now, what could go wrong with a compass besides the magnetism of the needle? Well, one thing is that it might, because of the magnetic field is not level, sometimes it dips. It may also have some error in it how it's made with the card. So here on the underside of the compass, what do we see? It's sealing wax. They
Yeah,
put
we're not
globs of sealing wax.
We're not dealing with like one that you could pick up at the dollar store tomorrow, right?
By trial and error to make it balance better on its point. The inside here, I can try to show you. Here's what it looks like. It's a ball. It's made of
Who's this kid in the sweater?
brass, because you don't want to use something magnetic, clearly. And then the pivot on this compass is, there's a little stone in there, like a piece of agate. It's like
Why is she saying compass like that?
So that's where this pin is sticking up against that polished stone to make it
Sounds like a regional
more
accent.
frictionless. Obviously, it has some friction. And so here's our compass card that goes in, and then we have this glazing to protect it, and then the box top.
Well, we all know we need a good glazing.
Have you look at this compass. This is from about the 1820s. So this is what's called a telltale compass. You're reading it upside down, and you can see that the point is coming up like this. And so this would be hung over the captain's bunk so that he would know when he's there what way his ship is going.
So while he's glazing, he can. Yeah. Oh, okay. All right. That's just okay. All right.
Going, even though he's not on deck. That's why it's reversed.
Okay, we have how to use a compass at Camping Cooks. Compass, a New World Encyclopedia. Compasses seem way more boring, I'm not gonna lie. Let's get the encyclopedia. Do. We'll get the GIS, geography on the difference between magnetic north and geographic north. That's kind of cool. Telltale compass properly mounted up from a ceiling from the Smithsonian, which is broken. Pages on compasses and there's Wikipedia. All right. So we covered that. Laser light wavelength determined meter. Oh, that's the Wikipedia article. We looked at that already. Navigate is to predict. I think we watched this. I don't know if there was anything else. No, okay, we watched that. We're good. All right, I think we're back on track. Okay. Sundials and astrolabes. Oh, there might be a video on sundials. Let's double check that one. Yep. Okay.
Another kind of navigational tool is an instrument for finding time, not just by the sun, but also for finding the times of tides. And these instruments would be used on land. They're not the type that would go on a ship. There's different kind of sundial you would take on board a ship. But I wanted to show you, these are both ivory sundials. They come from Dieppe, France, which is a coastal area. And so they're pocket sundials. And when you open them up, there's several different faces on them.
And they're made out of ivory?
And that you can find the time using the compass, using a string, using a little pin that sticks out of here. And you can also find time by moonlight using this dial here, which shows lunar phases. But the other thing this dial does is it allows you to find the times of tides. So on the back, this has a perpetual calendar, and it also has a calendar scale with a little finger pointing. As you turn this, you set that to the date, and then that shifts the silver hour scale that's inside the compass box. It shifts it up and down. And so when you turn this so the shadow of the top falls on the bottom, you read the time with the compass needle. It's a very unusual type of sundial. You can also set it like this and to your latitude and have like a little mini Earth. This would be in the equatorial plane. And so it's like the North Pole is casting a shadow. You'd be wealthy to own that one. Now here is
Yeah, no shit.
what.
It's made out of ivory.
So on this one, if you look on the back, you'll see instead of just a pointing finger at that, you have a whole person is pointing, like this is how you set it. Calendar scale, all sorts of other scales. This is it's what we call an equatorial hour scale, and it would work like that top of that, but it also has names of places all around, so you could see like the time difference. So if you were in Canada versus the Philippines and so on. This one's made about 1650. This one's made about 1660, 1680. Now this one has a coat of arms here of Henri Dorleans.
Alex in the chat conspiracy theorist. How did people build the pyramids? Ancient humans built astrolabes out of ivory. Yeah, I know, right? Like, I don't know why people think ancient people were stupid. Because they're not. They really weren't stupid. Like, what the fuck?
Orleans, who was a member of the French royal family. And
Morgan Porgan says, I heard that Canadians are just crazy Brits that want more snow. Not quite. There's a solid amount of, like, French undertone.
Duke. So when you're a member of a royalty, you get a big one. And so when I open this, it's the same as the little one, but just much more elaborate.
Much more elaborate and a lot more ivory. Jesus Christ. Because modern people are stupid. Yeah, I think that there's a lot of people around the world that live in like first world countries that don't value education as much as they should. That's something we remember we were talking about Vic Mignogna the other day, and he was like, "Oh, we take these things for granted." Education is something we take for granted, and we don't do a whole lot of work to try to improve regularly, which we should be doing.
Both of these have a chart, tells you like not only latitudes of various cities, but like whether there's a school, the highest ranking clergyman, and and a place to get horses for a road trip, and
Literacy.
Yeah. So I haven't cracked the full code. There's like a dozen columns. It's sort of a guide Michelin, the Let's Go Europe of sundials.
Yeah, so we got How a Sundial Works from Yale Scientific. So if you want to check that out. We've got... Oh, I didn't mean to close that. A more detailed description of how sundials work from the British Sundial Society. Broken. Oh, so it's probably still around if you want to go find more, but here's the link. It's been a long time since I watched a stream where the creator is watching a video and it's not riddled with science denial or political misinformation. I do my best on these streams. We're here to learn. We're not here to debunk. We're here to get the knowledge to make it so you can debunk. An unusual timber sundial at the Sydney Observatory. What? Okay, I don't know about that. It didn't work. The equation of time used to reconcile the actual reading on a sundial with the mean solar time, which assumes that every 2 noon times are exactly 24 hours apart. Oh, look at that. Remember we were talking about graphs earlier? Somebody was like, hey, graphs? Hey, we got graphs. There's graphs. Look at that. Look at this. Look at all this math I can't read. Neat. make some of this stuff at work for some reason, hell yeah, do it, man. You do that shit. Show it to me if you can. Like, I'd love to see whatever you work on. Like, if any of you guys make any of this stuff, like if you guys like make an astrolabe, please send me a picture of it. Tag me on Blue Sky or something. Like, I would adore to see that. Oh, we got graphs. All right, well, here's that Wikipedia article for the equation of time. Trigonometry. I don't understand most of this. I'm not good at math. There is one or two math courses inside of the stuff that we're doing. So yeah, if you make a stun dial, a stun dial, I would like to know what a stun dial is. So if you could make one, that'd be great. But if you make a sundial also, I'd love to see it. That'd be super cool. All right, back to business. I'm gonna go back to the top of this paragraph, and put the music back on. This is Club Penguin. You guys hear it okay? That should be fine, right? Of speed's numerator and denominator, distance and time, it's historically been harder to measure time very accurately. Over the centuries, many technologies were developed to try to capture time. Sundials and astrolabes are at least 2,000 years old and were used on ships into the 16th century. Sandglass were used from the 14th to the 19th century, but were highly affected by changes in humidity. Mechanical clocks, as we know them, were in no way up for the physical and weather conditions of a ship until nearly the 18th century. Let's check out Sandglass. Sandglass, also known as an hourglass, sand clocks, and sand timers, are among the oldest time measuring devices. A blown glass structure allows sand to flow slowly from one bulb to another. Each glass may be slightly different, so proper calibration is important. Manufacturers would adjust the amount of sand inside or mark appropriate times on the housing of the glass. While sandglass can be fairly accurate and reliable, they are not useful for long-term timekeeping. The simple need to keep turning them and the introduction of human error into that process necessitated the use and development of other timekeeping methods. In use at least as early as 350 CE, possibly invented in Alexandria in 150 BCE, used for navigation from the 14th to the 18th centuries. In modern times, they only see occasional use in kitchens as egg timers and in board games. Yeah, we could use more of these around, mostly because they're cool looking. Oh, we got video! Let's go!
They had a sand glass, specially made like this one. Oh, this is a little log glass. They're called log glasses. They would measure about 28 to 30 seconds. You can see it's in a protective covering so that it wouldn't get damaged at sea. And it was supposed to be accurate too within a second. It's not until the 19th century that they can blow it as a single piece. So they actually have two glass vials that and like a sieve between them, a pierced bit of metal, and they stick them together with some sand or ground up eggshells or whatever they decide is going to be the material inside. And then they cover that with string and wax and cotton and wrap it all around in the center. And that's the sand glass. And they put in a housing so that you can flip it and protect it.
I mean, pretty straightforward. How does an hourglass measure time? From the Library of Congress. We have how hourglasses are made, which I want one of these. I need to make one of these. I should make my own. Wikipedia on marine sandglass and hourglass, and Museo Gallio's page on hourglass and water clocks. I don't know if I'm pronouncing that correctly, but there you go. Instantaneous speed measuring devices like chip logs require measurement of short time spans and simple human counting off of seconds, as in 1 Mississippi, 2 Mississippi, can suffice for rough estimates, but for navigational systems that rely on timing of particular celestial events, like the sun's passage through its highest point in the sky, how accurately one can measure the position on the sky of astronomical objects becomes a key determinant in how well one can measure time and, in turn, speed. Yeah. If you're wrong by a little bit and you don't check it and you're not regularly doing that calculation, you are going to get off. You're going to get off course really fast. But what time is it? Days and hours were important units by which to measure time, and the movement of the sun across the sky was used to define these units. The division of the day into 24 hours is thousands of years old and derives from the Babylonian sexagesimal number system. These hours, however, have not always been equal in length. Up into the Middle Ages, days were often split into daytime and nighttime, designating 12 hours for each half. For those who did not live along the equator, the length of these hours changed with the seasons. Such an approach may seem odd when we look back from a culture which devices keeping precise and standardized time to the second pervade day-to-day life. However, standardized time and time zones and affordable clocks capable of long-term synchronous timekeeping are all less than 150 years old. That's kind of crazy. That's kind of like less than 150 years old for standard time and time zones. Unlike clocks today, or the cell phones in millions of pockets, the time that has been kept for most of human history has been local time. And local time was calculated using the sun, which is why local time is also known as solar time. At the highest point of the day, the sun crosses the local meridian and appears due north or south, depending on latitude. This is called local apparent noon, and was used for centuries both to measure latitude and synchronize timekeeping devices. That makes sense. Sailors at sea used this midday measurement in combination with sandglass or other technology to count the hours of the day. Earth's eastward rotation causes the sun to appear to rise and set and reach its noon peak in the east before it does in the west. And so local time is determined by an observer's longitude. Because the Earth rotates... That's Dapper, by the way, pinging me. It's not Mania this time. I just didn't know if he was going to do Kent with Bent today, or if he was going to be stuck with me with Tisdale Tuesday. So, it is Kent with Bent later today. Where was I? Because the Earth rotates at a rate of 15 degrees of longitude per hour, thanks Bob, or 1 degree every 4 minutes, the sun rises over Greenwich, England at 0.0077 degrees west, about 4 hours and 44 minutes before it does in Boston, Massachusetts at 71.0589 degrees west. This means that the local time in Greenwich is about 4 hours and 44 minutes later than that of Boston. Wait a minute, my cell phone says that the time difference between Boston and Greenwich is exactly 5 hours, not 4 hours and 44 minutes. This is because we now use standardized time zones that center on every 15 degrees of longitude. Boston, at about 71 degrees west, is 4 degrees east of the center of the Eastern time zone, 75 degrees west, which means that the sun rises over Boston about 16 minutes earlier and that Boston's local time is about 16 minutes later than Eastern Standard Time. This 16 minutes, or 4 degrees of longitude, account for the difference between the standardized time on your cell phone and the local or solar time. This physical relationship as well, as we'll see later on, was essential for determining much more than time. That's super interesting. Yeah, like we get hashtag thanks, Bob. Greenwich? Is that supposed to be count Greenwich? Man, come on. What am I supposed to do with that? What am I supposed to do with that? Come on. That says Greenwich. There's an N in there. I'm not crazy. Greenwich. Ugh. Greenwich? Alright. Fine. Footnotes. Oh, there's lots of footnotes. Ooh. Okay. Very cool. The magnetic properties of metals like lodestones have been known for at least 2,000 years. Why do I think that the footnotes are going to be like the test? Greenwich? I don't know. Guys, what do you think? Keep in mind what you think is going to be on the test, because I got to write that shit down. The magnetic properties of metals like lodestones have been known for at least 2,000 years, though their application for navigational instruments seems to arise only after 1000 CE. While magnetic compasses are extremely useful for quickly discerning magnetic north, the Earth's magnetic field is not exactly aligned with its axis of rotation and furthermore changes over time. This is why we should all be using the fucking universal fucking atom clock or whatever the fuck. I forget what it's called already. Whatever. Well, magnetic compasses are extremely useful, and Bob, I just read that. Oh my god. The difference between magnetic north and true or geographic north is known as magnetic declination, or to navigators as variation. The variation of the Earth's magnetic field changes in relation to location and even far away from magnetic poles, can be as great as plus or minus 20 degrees. The smaller magnetic fields that can exist around metals like iron and steel also affect compass readings. This interference is called deviation. Something small like a belt buckle can be easily avoided, but on a ship loaded with cannons, ammunition, and 1-ton anchors, the deviation is unavoidable and, moreover, changes depending on heading or the direction the ship is facing. While the magnetic compass was a great aid to navigation, it required consistent corrections for variation and deviation and only realized its importance in relation to speed and position. Goblin munchies time? That apple made me feel kind of full, but it made me also still hungry. I don't know what that's about. I don't have a good relationship with fruit, it seems. I prefer vegetables. Like, I would rather eat a carrot. But, I mean, I like apples. Like, they taste fine. But, like, I felt full while I was eating it. Now I'm, like, hungry. My gut is like, feed me. I'm hungry! Hold on, I have a thing for this. Hold on. Fucking hilarious, man. I'm gonna pull it up. Hold on.
Good night, baby champion.
Don't touch me. Oh,
Don't touch me.
now I'm so sensitive because I'm so hungry.
Because I'm so hungry.
Yeah, I'm hungry. I'm hungry.
Always hungry.
I'm hungry. 배고파.
Good night, baby champion.
Don't touch me. Oh,
Don't touch me.
now I'm so sensitive because I'm so hungry.
Because I'm so hungry.
Yeah, I'm hungry. I'm hungry.
Always hungry.
I'm hungry. 배고파.
I'm hungry! I'm so sensitive. Feed me, Seymour. Yeah. Alright, footnote number 2. We tend to think of maps as two-dimensional paper representations of three-dimensional space. Do we? I don't think we do that. I don't think people do that. I really don't. Like, I mean, Google Earth makes that pretty clear, but like, I don't think most people, if you hand them a map, superimpose it on a 3D space when they think about it. Do it. Do it. Do it. Send it to me. Tag me. I want to see it. However, for Polynesian navigators and Australian Aborigines, space was represented through story and or song. Paper, invented in China, didn't reach Europe until the 11th century. Really? Bro, like, what? How did... China was just fucking ahead of the game, man. It's because they started writing shit down so early. So we were like, yo, we gotta write this shit down. What are we writing on? Doesn't matter. What are we using to write? Doesn't matter. We gotta write shit the fuck down. I guess China was also like also gravely different when it came to like, by the time, like far enough away from like England and Spain and France, and like not attached to the Roman Empire. And like also you've got like, I mean, India was doing amazing work in mathematics, and we just ignore that a little bit. We shouldn't, but like they were way ahead of the game in mathematics. Anyway, paper was invented in China and didn't reach Europe until the 11th century. I didn't know paper was invented in China. Accurate cartography was difficult and nearly impossible on a large scale. Latitude could be determined well through celestial observation and measurement, but longitude was elusive. This resulted in maps being relatively accurate in the north to south dimension and much more skewed east to west. That's fascinating. Today, you are an inheritor of oral cartographic traditions. The constellations in the night sky, their names, shapes, and stories are similar mechanisms by which to remember specific orientations of stars as well as their movements through the year. The earliest known unit of length, what is called a cubit, what is today called a cubit, was used in ancient Egypt and Mesopotamia and was based on the length of the forearm from the elbow to the tip of the middle finger, or in some cases to the wrist. Similar forearm measurements were used in China, Japan, India, Greece, and Rome. Some of these measures, as well as the Egyptian and Mesopotamian cubit, were inscribed on sticks and rods for somewhat standardized use. Smaller units of measure added up to larger, abstract measurements that still had a base in human-sized length. While the Greek stadia was about 2 football fields. Why are you telling me it's about 2 football fields? Why aren't you telling me what it is in, like, meters? Well, how big is a football field in meters? Or, it's... Fuck you! Football field dimensions. You fucking dicks. "120 yards means nothing to me. 360 feet means nothing to me. 109.7 meters. I fucking hate you. Why is it 109.7? So 110. I'm just gonna call it 110. So that'd be 220. There's 2 football fields. I'm assuming 2 football fields in length, right? Not width? Is that correct? God. The Australian football field? I'm assuming it means, I mean, this is Harvard, but like, they've been so good about telling me what things are in like meters and shit. Why is this one in why are you giving me 2 football fields as a reference? How many fucking deer is that? God. This is why everybody makes fun of you, United States. Stop doing this. Cease. Look down here. Feet or miles. Immediately. Like, an actual measurement. Like, can you... Oh. we still measure things by like human reference, right? Football fields is like relative to a person. Cups, a pinch of salt, things like that. We measure stuff like that all the time. Like that's never gonna go away, and I don't think it should necessarily. Fucking, you are 6 apples tall. Well, the Greek stadia was built up from paces, steps, and feet. The Netsilik unit Inuit of Canada's Nunavut territory measure long distances in sleeps or amount of times one would sleep over the course of such a journey. We still do that in Canada. I had no idea that that came from Inuit Nunavut stuff. That's a thing that we do, all, like, regularly. So it's like, oh, how many sleeps until Christmas? Right? So we're counting days, but, like... And then there's people will argue about, well, no, the day hasn't gone by yet because I haven't slept yet, so it doesn't count. I have no excuse for butchering Inuit. Yes, I do! I'm from Southern Ontario! In fact, it would be culturally inappropriate for me not to butcher Inuit words. Sheep units. 1 football field is 1 ISS. Gotta go get that washing machine started. Hey, right now, if you haven't drank any water today, or had a snack, you should do that. Also, do a chore while you're here. The word mile is derived from the Latin millipecium, which means 1,000 paces. Roman legionnaires would count their steps as they marched and thereby measure distances between locations. That's actually really smart because, like, the marching order would be pretty strict, I assume. Units of measure differed from region to region. It would be really funny if they didn't march in time and they all just counted on their own and then they all wrote it down, compared notes, and they took the median. Southern Ontario, I was there in 1996. Could we have met? You don't look that old. How old do I look? Oh dear. Here we go. Here it goes. Possibly. I doubt it. But it's possible. Southern Ontario is relatively large. Units of measure differ. There's also no, like, delineating definitive line between what is Southern Ontario and what is Northern Ontario. Like, that's not a real line. It's just, like, an arbitrary vibe check. Units of measure differ from region to region, even town to town, and units of the same name by no means measure the exact same length. Or the same exact length, sorry. These differing systems resisted standardization until 1886, when the majority of the Western world adopted the French-sponsored metric system. This is a piece of information I actually knew, because I looked it up before, because somebody, I don't remember who, somebody was like, no, the Fahrenheit and the imperial system make the most sense for, like, how things feel. And it's like, no, that's just because you're used to it. Ridiculous. And abandoned the human-centered measures for 1/10,000,000th of the length of the meridian passing through Paris from the equator to the North Pole. Today, a nautical mile has become even more precise and is defined as 1,852 meters, 6,076 feet, or 1.1508 miles. Other measures, those counted on ships themselves, retain the body-centric method of old. A fathom, for instance, was used to measure water depth or lengths of rope and line, and was defined as the length fingertip to fingertip between a man's outstretched arms. I love people trying to justify the imperial system. I know, right? Ugh. In school, we used to measure dinosaur size in school buses. You know, I feel like I remember that. that seems familiar to me. Like they would have the actual number and then they would put school buses beside it to give you like a relative information, like some context for how big it was. The speed of a ship relative to the water is measured in units called knots, which today describes nautical miles per hour. The knot derives its name from the 16th century method of measuring in which a ship's log, common log, or simply log, was tied to a rope knotted at specific intervals and thrown over the stern or the back of a ship. The log would drag in the water, maintaining a position approximately where it landed, and the ship moved away. The knot rope would unwind. One sailor would hold the rope and count the knots passing through his hands in the certain amount of time, thereby determining the ship's speed in knots per unit time. So, you know, not the most accurate thing, but pretty cool. Alright. Longitude prize and GPS. Navigation is the art and science of figuring out where you are and how to get somewhere else by way of intended course. The history of navigation is in large part, the story of instruments and techniques that increase the precision of measurements and position, speed, and time. 2,000 years ago, the known world was boxed in on all sides by water. 200 years ago, people were uncertain exactly where even the most scientific advanced cities were in relation to each other. 2 decades ago, humans had landed on the moon, and 2 years ago, while millions of people pocketed smartphones capable of pinpointing their location to within a few meters, humans landed a spacecraft on a comet, and the US Navy reinstated its celestial navigation program. The navigation technologies of today and tomorrow are descended from this multi-millennia quest for finding longitude on Earth, which itself derives from an even larger history of human movement, measurement, and prediction. And here's a space.com article about landing on a comet, because we're cool like that. Neat, right? The Longitude Prize. In 1707, Admiral Sir Cloudesley Chauvel, maybe, commanded the British Navy in an attack on Toulon, France. After failing to capture the city, Chauvel was ordered to return to England with his fleet. They never made it. On October 22nd, Admiral Chauvel's flagship, the HMS Association, struck rocks along the Sicily Islands. HMS Association and 3 other warships sank, and in what was recorded as one of the greatest maritime disasters in British history. The sea claimed the lives of Chauvel and nearly 2,000 sailors. The disaster was attributed to the inability to precisely calculate the longitude and contributed to Parliament's 1714 Longitude Act, which established a reward of £20,000, over £2 million today, for a reliable method to measure longitude within half a degree of about 30 miles.
I don't completely understand what the relationship between the Royal Society and the Royal Observatory at Greenwich was at that time.
First, I think it's important that astronomy was the first science to really be professionalized in any sense, apart from maybe medicine. In 1675, the Royal Observatory was set up, and of course other countries set up observatories about the same time, and they had fairly big instruments and they had professionals, and of course there weren't professional physicists or chemists at that time, and so that's why astronomy was the first science, and that's why incidentally there is this title which I have called Astronomer Royal. Right. There's no physicist royal or chemist royal, because the first government supported chemists were not until the 19th century, when they didn't use these anachronistic titles. So the Royal Observatory was the first sort of government supported scientific establishment, as it were.
I like how flippantly he's just like, this is anachronistic.
Of course it obviously had links with the Royal Society, and of course the other important scientific endeavours were the great expeditions, Captain Cook's expeditions and others to observe the transit of Venus. And that was really very big science by the standards of the time. And these involved the Royal Society, and they involved astronomers. The Royal Society was the body that oversaw the whole of science, but clearly it took a special interest in astronomy at that time. The Longitude challenge was identified in 1714. There was a Longitude Act set up, and they set up a board of longitude, and Simon has done a great deal of work on the archives of this board, which existed for more than 100 years to support and reward innovations of all kinds. But the famous challenge was, of course, the Longitude challenge, and this involved astronomers, and of course the challenge was eventually won by chronometers, but of course the astronomers were involved, and there was a lot of tension because the astronomers in many cases favoured a different technique.
When I say that human beings are part of drama and do drama all the time, and it doesn't matter what field you're in, nobody's better than anybody else. Astronomers will fight with physicists, physicists will fight with chemists, chemists will fight with other chemists, chemists will fight with fucking biologists. Like, everybody's constantly got beef with everybody else, and it's like one of my favorite things about humans and about academia is like, there are always academics fighting with other academics, either in their field or at those intersections, or like, you know, competing universities. Like, this is one of those things where like we don't need capitalism to be competitive. Humans are competitive almost inherently in a general sense. Like, there are individuals within the group that aren't or don't care that much, but humans as in a general are competitive by nature. So like, we don't need capitalism to be like to make us be competitive. We do that anyway. We make that shit up on our own. People constantly regularly challenge themselves to no monetary benefit at all, right? So like, it's motivating for a lot of people. So it's like, it's fucking silly. But yeah, no. Anybody who's like, oh yeah, no, I'm above drama, they're lying. They're fucking lying. And in fact, the people who are like, oh, I'm above the drama are probably the ones stirring the pot and sipping the tea and watching shit go on. Those motherfuckers. Fucking liars.
From measuring the position of the moon, etc., and Maskelyne, who was the astronomer, became the astronomer royal while this was going on, was a strong proponent of that, and was thought therefore to have a special interest in a particular solution. So that's a way of saying that astronomy was involved with the Royal Society, and the President of the Royal Society was ex officio on the Longitude Board, along with various government dignitaries.
I definitely am a pot stirrer, but I don't claim to be above the drama. I don't pretend I'm doing something I'm not, you know what I mean? Alright. That was the Longitude Act. The millennia-old problem of longitude was integral to the construction of the Royal Observatory at Greenwich. Get out of here.
Can you guys talk a little bit about what the founding of the observatory itself had to do with the quest for longitude?
Everything. That was it. Right. It was to provide the astronomical data that mariners could then take to sea with them and use to determine their longitude at sea.
And the other thing is, it was a scientific endeavour, you know, a practical problem, but there was also this sense of international competition.
Yes.
Somebody had told Charles
Especially
II, the French were doing this, they were mapping the heavens.
Right.
And so the idea that this is critical, it's almost a military secret.
The Brits versus the French, go figure.
Secret, right, to have a decent star map. and the ability to navigate.
Well, in the U.S. it is the Naval Observatory
Well,
that
exactly.
was charged with doing this.
And indeed, the Navy ran this place for many years before the astronomers moved out in the 60s.
But so what was Flapsy doing paying for his own instruments if this was so incredibly important?
Well, very important, yet everything was done on a shoestring budget. When you look at...
the room does not exactly look like a shoestring
It doesn't,
budget.
does it? But,
No.
but all is not as it seems, because if you look at the panelling in this room, it's actually pine simulated to look like an expensive hardwood.
Really?
Yeah.
So, and
That's funny. I like that.
the money, believe it or not, was raised from all manner of things, including the sale of damp gunpowder. So Admiralty clearing out redundant sort of stock from the stores.
Does damp gunpowder dry out?
Materials were recycled. Well, yes, actually, the merchant who bought the gunpowder dried it out and made a good thing out of it, selling it back to the Navy later on. But that's really sort of extra to the history of the observatory.
But what comes down is an instruction from the Crown that the Navy should do this, and some little bit of support. But otherwise, a general sense that this should be done, must be done. In fact, but not enough funding. It's beginning to sound familiar.
Yeah, I gotta love that. Hey, we really need to do this. We're not gonna give you any money to do it, though. It's really important, but you can't have any money. Hey, NASA, does this sound familiar to you at all?
Yes.
And so, it's an old site that was available. We're on the foundations of an old castle, so that saves quite a lot of money.
Yeah, forget about that whole north-south.
That's right. You make compromises to create a working observatory.
But when you think of the observations that were done from this room, I mean, there were observations of the sun in conjunction with the clocks, observations, no doubt, of bright stars in the northern sky. This room was important, but when it came to cataloguing the stars, that is, providing the charts of the night sky, that had to be done outside because, of course, the lovely ceiling does get in the way. But
I wonder how much, like, photography, like the ability to take pictures, like the first camera fucked with any of this. Or if it was, like, too late in its arrival, its invention.
surprisingly, though, this room was used for astronomy right the way through the history of the observatory, even in the 19th century.
I have a suspicion that it was used to show off for visitors. This is where if you had the first Sea Lord or something coming to inspect, or a royal visitor, I'm sure that you would have sent a telescope.
That's a very interesting point, part of the pomp.
That's right. And in fact, that's in the founding of the observatory, that there should be provision for the astronomer royal to live so they could do science, but with, I think it says, a little bit of pomp. And so this is the little bit of pomp that we were allowed as astronomers. We get pine, but it looks great.
So when we see prints of the observatory with a great telescope sticking out of this window here, maybe it's because there was an admiral coming to visit.
I'm sure that people have been playing this game for centuries, but it is that sense of this is a public thing. It's not just doing these observations, but being seen to be leading.
And so, if we look around the room,
tying your science and what you're doing to your populace and getting that benefit back and forth one way or another, that clear communication I think is really important to advancing science because it makes it worthwhile for the people that it's supposed to be benefiting.
Then, how many people would have been? Would you bring a party of important visitors in here?
I'm guessing, but I would think so.
You think?
I mean, on a normal evening, the staff at the observatory wasn't large. In Flamsteed's day, it was Flamsteed and a couple of assistants, I think?
Well, he had his assistant, Sharp, and he had household staff as well, and his family.
And I know that a lot of the royals and aristocrats were very into sort of studying different subjects that interested them. And so when you have people coming in here in the 16th, 17th, 18th century, not the 16th, sorry, the 17th and 18th century, would they have understood really what was going on? In other words, the details of why it was that this should have been north-south and what the quadrant does? And
some of them would have done it. I mean, I think probably the best source of that is looking at the Royal Society records and people who would go to these discussion meetings. So there were certainly some quite heavy, some quite learned discussions, and certainly people like Pepys, the diarist, complaining that he doesn't understand much of this stuff, despite the fact he's president of the Royal Society.
Okay.
I mean, his name's on Principia, for example, but it's not clear that he actually understood any of the maths that's in there. And so it's a mix. I think, and certainly the...
Yeah, sometimes the people who fund the thing that you're doing don't understand the thing that you're doing. That's the whole point of having, like, being, like... Sometimes it's important to know when to step back and let somebody else fucking do the thing. Like, the whole point of, like, having resources and resource management is knowing who needs to be in charge of what. The millennial-old problem of longitude was integral to the construction of the Royal Observatory at Greenwich, and inspired Britain's best and brightest to attempt solutions. Among those who sought to solve the problem of longitude were some of Britain's preeminent scientists, members of the Royal Society, Astronomers Royal, and an unknown clockmaker from a little village in Lincolnshire. Dude, one fucking random clockmaker dude was in on this. That's the guy the book is about. Like, when there's a book, like, when there's a fucking fictional, historical fucking novel about it, it's about this guy. Well, it was generally agreed that the solution to longitude lay in knowing the time at two distant locations. The methods of coordination varied greatly. Astronomers believed that the answer was the moon. Moon! An idea that dates back to at least the 2nd century BCE. Britain's first two astronomers royal, John Flamsteed and Edmund Halley, laid the groundwork to using the moon by meticulously compiling accurate star charts and improving the predictive tables of the moon's movements. These tremendous achievements paved the way for Neville Maskelyne to finally develop a sufficient, precise, and reliable lunar methods. And we get a video.
Let me ask you what you think the relationship between what was going on kind of completely empirically and trying to make better charts and better predictions about the positions of things that could be used for navigation, and then the understanding that came later with Newton. Do you think that that was important in terms of appreciating what it meant to try to solve for the motion of the moon and that kind of thing?
Well, it was absolutely critical to the work of the astronomers here. I mean, it was really Edmund Halley who was...
Halley.
Flamsteed provided the first improved catalogues of stars, and Halley, already with a proven track record of predicting motion with Halley's comet. So he was a natural candidate to try and pin down the rather complex motion of the moon. And his work goes
and actually to
quite
get
deep.
The time series right, so it's 1676. You said this.
So, yeah, well, that's
1687 is Principia, but Newton actually was doing the work probably at
That's
before
right. But what
1676.
Newton's not doing is this sort of big science, right? Newton's an experimenter. He's doing his own thing. He's writing up his own results, whereas here we have a longer purpose, right? They're planning for decades of work in mapping the stars.
That's right.
And so it's more of it's all in modern astronomy terms. Here they're working in survey mode.
That's right.
Right? They're producing a data set for others. Newton is a sole experimenter.
That's true, but we should say that the central purpose of this data set was to be able to improve celestial navigation.
Absolutely. I mean, this was the lunar distance method.
Well, and stuff like that is a matter of, like, just a lot of time and a lot of being, like, incredibly particular and accurate and consistent. As opposed to, like, flying a kite and getting it hit by lightning, you know what I mean?
It was known to be a viable solution in the 1500s. It was not a new concept, but it was having the data and having the tools, the equipment to provide that data. And the clocks here provided that first proof that the Earth's rotation was, well, for the best intents and purposes, was at a constant speed, which of course you need.
I have a question about Jeranism. So Jeranism was, well known for being a flat earther, and now he's not a flat earther anymore because he went to Antarctica. Long story short. Does he now agree with or understand the math? You know what I mean? Like, is that... Has anybody... I haven't really seen... I haven't gone looking to see, like, what he's been saying or what's gone on with that. But But like, is that a thing? Also, I just wanted to show you guys these. These are Hawkins cheesies. So these are Canadian cheesies. They are so fucking crunchy, like they're so fucking crunchy. They're also very, like, they're corn-based, I guess. But Canadian cheddar cheese. Per 1 3/4 cup is 280 calories. 450 milligrams of sodium. Nom, 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 nom. They got 3 grams of protein. What the fuck? Cornmeal, vegetable oil, processed aged cheddar cheese, seasoning, lactic acid, disodium phosphate, salt, and certified color. They're fucking good. Nom, 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 nom. Nom, nom, nom. He accepts the math now? Does he understand it a little bit more now? 15-degree drift. Thanks, Bob. Yeah. You think he tries to? Oh. Well, at least he's, like, now open to trying to understand it as opposed to being, like, a dick about it. Nom, 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 nom. All right, back to this.
To be sure of before you start making charts and yeah.
I think really the thing that was harder to tackle was how to translate that method. It's almost a science communication problem because it's one thing for the astronomers here to be able to calculate distances and positions based on observations of the moon with this setup around them. It's another to be doing that on the deck of a ship
and to be doing the math
around
without
the
completely
seas.
understanding what you're doing.
Right, exactly.
Right, yeah,
and so that was always the criticism of the astronomers' distance method. Of course, it could have been a great source of employment for astronomers if you needed to take one to sea with you. And a few people did.
By the time that the lunar distance method was a practical reality, the mathematics required to calculate your position in the early days took about 6 hours, apparently. And, you know, in 6 hours, well, fortunately, ships weren't going that fast, perhaps,
But nonetheless, it's not ideal.
No. And what was I going to say? Well, I'll be able to show you later that we've recreated what you need to do for the lunar's method.
Yeah, that's a really good point. Having to do all of the math by hand and how long it would take to go through and do all of the math and measurements is, like, seriously underestimated. I think I need Canadian snacks. Oh, yeah. Definitely get some Canadian snacks. These fuckers are good. You do have to get used to the salt. These are even, like, a little bit too salty for me to eat too many at a time. So, like, they do slow me down. So I'm not just, like, munching the whole bag. But the, I definitely recommend them. Get yourself a Nanaimo bar. Those fuckers are good too. I'm hungry! At least you're hungry? Yeah, that apple made me hungry. That apple made me feel full, but then feel hungry at the same time. It was weird.
Showing how it works in worldwide telescope. And so I'll show you later. And even just to understand what you're seeing there is complicated, never mind doing the math. But it was an American, right, Bowditch, who made a simplified way to do those calculation of lunars, is what I understood from an American navigator friend. Is that not true?
Yeah, I don't know the specifics
I think
of
it's
that.
in the
That's a little
1800s.
beyond
It's
the
much
sphere
later,
of my,
yes, anyway, it was very complicated.
By which time the story here has moved on to clocks and to Harrison and to the other methods of determining position.
And that was when the clocks got less expensive.
The timekeeper being a very obvious, easy way, which you know, you need to know how to determine local noon using astronomical methods, of course.
That's right.
But otherwise, you just compare. Then you just compare that to the going of your
The local
your
noon
clock or
part
your watch.
is awfully easy compared to the lunars.
Definitely.
Yes.
Both methods, though, do rely on having.
Was that a thing with why, like, when movies are like take place in this time period, why people have pocket watches, but not everybody seems to have a pocket watch. Only like the nicely dressed fucking people have pocket watches because like the rabble didn't get them.
Clear skies.
That's true. That's true, but we sort of get this scientific bonanza by accident, or at least incidentally to the main thread. If we were telling the story just of navigation,
Right.
you know, we'd have this lunar method that was complicated, that involved astronomers, and then you get noon, and the timepieces catch up, the clocks are the limiting factor. But actually, on the side, you've created this wonderful star catalogue, you've had a whole series of people who've made impact.
Every time we do science and make scientific advancements in one thing, we are advancing science in other ways and inventing things in other places. Every single time. Just look at them going to the moon and how much shit came out of, like, going to the moon.
In other ways, in understanding the heavens, and astrophysics gets going.
Right. Yes.
Out of those foundations, people start to study the sky instead of just to map it. So, but really, that's almost irrelevant to what people thought they were funding here.
That's true.
And what they thought they were doing.
That's interesting. It does seem to be the case for kind of everything. Which is neat. Neato burrito. But Neville wasn't the only one to crack the problem. Though the best clockmakers and thinkers at that time considered mechanical solutions impossible, a provincial clockmaker named John Harrison devoted his life to making accurate clocks that could withstand the harsh conditions of sea travel. In 1730, he traveled to London seeking financial assistance to actualize his designed sea clock. Harrison shared the plans with Edmund Halley, who referred to him as George Graham, England's preeminent clockmaker. The design must have been impressive, for Graham lent Harrison the money he needed. Harrison's work on the sea clocks, or what became known as chronometers, spanned over 3 decades, involved 4 different models, and grew so politically charged that eventually the King of England became personally involved.
Okay, well, so we're going to ask Rory to tell us about the clocks in a minute, but I'm going to play a fun game with you. I have a plan. I've thrown away my prepared questions. And so you're going to be the astronomer, and you're going to be the clockmaker, and we're going to solve the longitude problem.
All right, fair enough.
All right, so poor Admiral Sir Cloudesley Shovels has been lost at sea, and we have to do something about it, and so Sir Astronomer...
No, I'm a 17th century
and
astronomer.
it is the 17th
Well,
century.
clearly the most important thing is more astronomy.
Okay.
So what you need to do to solve this problem is give me more money so that I can understand the motion of the moon.
Okay.
And I'll need to map it relative to the background stars.
Okay.
So we're going to need to build a sumptuous observatory.
A little pomp.
With a little pomp
Okay.
here in Greenwich,
Okay.
so that I can catalogue the stars. And when I've catalogued the stars properly, you'll be able to observe the stars from on board the ship, have a look at the moon, and you'll know precisely
What about the
where you are.
wobbly ship? Is this going to be a problem?
Well, we're going to need to take astronomers on board ships as well. This is the problem. But we can train the sailors. That's fine.
Okay.
I mean, astronomy is, after all, a simple science. But the important thing is to get a better catalogue than the French.
Okay, how long do you think this will take?
I like that all the trigonometry and math is considered a simple science.
How much money do you have? I think we could probably get a decent catalogue in 5 to 10 years. But this is going to be an ongoing programme of improvement that will take decades.
And I hear that there are these clockmakers who think that they can do better.
Yeah, well, we think that the obvious solution is, of course, to take a watch with you, keep it set to your home time, and then compare that to observations of the sun at noon. Getting the time difference very easily, then you can convert that time difference into degrees around the
So
circumference
just
of the
use
globe.
the Earth as a clock.
But you still need astronomy. You still have to observe
You
the
do.
sun. And of course, building a clock that you can take on ship is very difficult. You've got all these
Well, this
giant
is-
pendula.
Well, this is a problem we're facing at the moment. Our best watches are, let's say, at best, we can get maybe 2 minutes a day. Accuracy to within 2 minutes a day. But the problem is we don't know whether that's going to be plus 2 minutes or minus 2 minutes or somewhere in between. And that might change from day to day.
So that adds up to sort of a few nautical miles a day, which means you're going to get lost pretty quickly.
Yeah,
And
so
if you're
predicting
sailing,
your path is not.
If you, you'll have a cumulative error, and within a few weeks, you really won't know how much you can trust them.
So how much money do we have to give you?
Hey, it's that cumulative error that I said.
We really do need to. We need to improve the watch.
Send me to the moon, motherfuckers! The moon's not real, and it's made of... Well, the moon is real, but it's made out of cheese. We're gonna get through... We're gonna get through this part, and then we're gonna take a quick break. Harrison's first design, H1, was built out of bronze lignum vitae, oak, steel, and brass, and stood 67 centimeters in height. Harrison had previously built clocks made completely of wood and learned to use different varieties that expanded and contracted at different rates to combat thermal expansion. Oh, I want one! I want a clock made entirely out of wood. That's cool! He brought this expertise to bear on H1, which required no lubrication and was unaffected by the rocking of a ship due to interconnected swinging balances. H1 was tested in a 60-mile voyage. Though it outperformed the sailing master of the ship, the short trip fell well short of the transatlantic trail required by the Board of Longitude. H1 showed such promise, however, that the board granted Harrison 500 pounds to continue its work. H2 took 3 years to build and 2 years of non-land testing before Harrison deemed it ready, which placed its unveiling squarely within the War of Austrian Succession. A testament to the importance of measuring longitude, the government deemed H2 too sensitive a technology to test during wartime, for fear it would fall into enemy hands. As Harrison waited for the war to abate, he discovered a major flaw in the balancing rods of H2 and abruptly abandoned the design. Harrison worked on his third model, H3, for almost 2 decades, though he never achieved the level of precision that he deemed necessary and eventually gave up the design. Harrison invented the bimetallic strip and the cage roller bearing in the process. H4 was a completely different machine. Wood and bronze were replaced by copper, diamond, ruby, enamel, and glass, and its overall size shrank to 16 centimeters in diameter. The sea clock had turned into a maritime pocket watch. H4 performed my brain is stuck. Guys, I got to the point where my brain started stopping. How am I pronouncing this? Phenomenally. My brain just stopped. Holy shit. H4 performed phenomenally on its I got stuck on this. Phenomenally. On its maiden voyage to Jamaica. However, questions about the rate of change in the timekeeper made another test necessary. In 1764, H4 sailed from Portsmouth, England to Bridgetown, Barbados. The trip took... Hey, isn't that where Rihanna's from? The trip took 46 days, and besides winding, holy shit, H4 was not touched after setting its local time in Portsmouth. Harrison, now in his 70s, could not make the voyage and sent his son William in his stead. In order to test the accuracy of the chronometer, the precise longitude of Bridgetown was needed to be known. The Board of Longitude sent an astronomer beforehand to make these measurements using observations of Jupiter's moons and to evaluate H4 upon arrival. Using Jupiter's moons? Not our moon, not Jupiter. Jupiter's moons specifically. Jesus Christ. The astronomer they sent was Neville. Wow, really? What are the odds? That must have been intentional, right? That's like the I know a guy, right? Neville or Neville, whatever. Mascaline. Had his own reasons for wanting to make the voyage. It was a perfect test case for his own work on the lunar distance measurement. The chief methodological rival to Harrison's clocks was that over 60 years in development. When Harrison's son arrived with H4, he heard that Mascaline's lunar had successfully determined longitude within half a degree. H4 was taken ashore for testing. As the sun reached its local noontime peak, H4 read the time in Portsmouth to be 3:55, which placed Bridgetown just under 60 degrees west and only a few miles off from its true location. After a month and a half of sea travel and 46 days since first being set, H4 had lost only 30 seconds of time. That's incredible. That's crazy. Holy! Upon returning to England to proclaim the success of H4, Mascaline was appointed the 5th Astronomer Royal. One of his first orders of business was to confiscate H4 for further testing. The beef! The drama. That is so fucking beef, man. These two are fucking fighting. While this may have been influenced by competition, his questions and those of the board made sense. When the best clock would lose nearly a minute a day, H4 had only lost 30 seconds in 46 days. Moreover, the wording of the Longitude Prize necessitated that the solution be practicable. In other words, could H4 be replicated? Until this was answered, Harrison did not see a pence. For years, H4 was held, a copy made and tested, and still Harrison saw no money. Finally, in 1772, Harrison's son wrote to and was granted an audience with George III, King of England. After hearing Harrison's stories, the king proclaimed that the wrongs Harrison had endured would be righted. And so, 43 years and 4 clocks after first traveling to London, John Harrison finally received the full Longitude Prize with only a little added pressure from the king. The beef! This dude stole his shit and held it for testing so he couldn't make any money. What a dick! Oh no! The 2014 Longitude Prize. Governments seek innovation to drive economies, compete internationally, and address the problems that can come with attempting to continually maintain and, more recently, improve human life on larger and larger scales. This compulsion to imagine and transform on national and international levels has contributed to the institutionalization of research and development, which includes scientific research establishment, think tanks, and the proliferation of modern universities, and a commitment to specialization. However, governments have also used state-sponsored challenges and rewards to push innovation, promote public understanding, and induce non-specialists to take a crack at some of the biggest problems and puzzles. The Longitude Act is a prime example of this enticement-based crowdsourcing, and others include the invention of canned food in early 1800s was the first transatlantic flight in the 20th century. Currently, some challenges remain unmet. Rewards still exist for nanosatellites, lunar rover designs, and diagnosis tools similar to Star Trek's tricorder. In 2014, a new Longitude Prize was announced, this time having nothing to do with longitude. The challenge offered a £10 million fund and an £8 million payout for a cheap, easy to use diagnostic for bacterial infections that will allow healthcare professionals to administer proper antibiotics and hopefully address growing levels of antimicrobial resistance. So if you are in any way inclined, hit the lab, get designing, and perhaps you can be the John Harrison of the 21st century. Do you want to be the John Harrison, though? That dude worked for fucking like 70 years and didn't get dick until the very end of his life. But yeah, I'll link you guys these things. The N prize. Hey, Canada's not in there. Why aren't we competing? So, yeah, if you're interested in the N prize for nanotech, there is the Lunar Rover Designs, if you're interested in that. There is the Star Trek Tricorder Diagnostic Tricorder X Prize. And 2014. Get out of here.
There's a modern new Longitude Prize from 2014, from the 300th anniversary of the British Longitude Prize, that has a similar goal of solving a big scientific problem, but it's being approached in a very different public-minded way. And so if you want to comment on any of that.
This is something which I sort of helped to initiate, just feeling we ought to commemorate this important historical event in 1714 when the government identified a challenge. This is, of course, not so original now, because there have been over the centuries a whole lot of challenge prizes of all kinds. I believe tinned food was the result of a challenge prize in the Napoleonic era.
Really? I didn't know that.
It was, yes, and I think the first transatlantic flight was also the result of a challenge prize. And I'd like to mention also, as a digression, that there was a prize set up by a French foundation in around 1900 for the first person to detect extraterrestrial intelligence.
Does that still exist?
100,000 French francs, but Mars was excluded. It was thought too easy to find it on Mars. So that hasn't been won yet. What we did just a year ago was to...
All right, well, if you want the French prize of finding intelligent extraterrestrial life, as long as it's not on Mars, you can win a bunch of French money.
Get government funding of £10 million for a challenge prize, and then to have some public discussion and a TV program, etc., on what the challenge was. The popular vote was in favour of some equipment that would be relevant to the big global problem of antibiotic resistance. Of course, you can't develop new drugs for £10 million. What you can do is perhaps develop a simple gadget usable in developing countries, whereby...
Stop the stupidities for 5 cents. I like money, though. Thank you very much. I greatly appreciate that. The money from Super Chats from these are going towards actually getting the certificates paid for, so I appreciate that.
People can identify whether they have a disease that is a bacterial or viral disease, and what it is, and to avoid, therefore, the overuse of antibiotics. And this is a challenge, and I hope we will get funding for some of the other challenges that were identified, like helping paralysed people, etc. I think the virtue of challenge prizes is that they can, in principle, draw in people outside the regular scientific community, the people who get grants, and also they can stimulate public interest. The antibiotic prize fails on those two criteria, in a sense, in that it's going to be something that only professionals can do. And that's why I hope, for instance, we can also get support for a national prize involving some kind of robotic challenge, because robotic challenges, as we know, have been done in the US, and they attract great public interest because you can see the robots getting better from one year to the next.
That's cool. The story of John Harrison, the marine chronometer, and the problem of measuring longitude at sea is integral to the history of navigation and the history of science more generally. For a more in-depth version of the John Harrison story with annotated table of contents, you can check out our fascinating conversation at the Greenwich Royal Observatory with the head of horology. I don't know if that's also supposed to be whatever. Anyway, these guys have a whole fucking thing about it. How long is this? It's an hour long. So that's gonna go off to the side for now. Okay, we'll put that off to the side and maybe we'll watch it another day. Longitude, relativity, and GPS. The importance of the relationship between longitude and time again made international waves in the 20th century when Albert Einstein proposed his theories for special and general relativity. Special relativity has to do with differences in time due to differences in relative motion. General relativity has to do with the differences in time due to differences in the effects of gravity. And both have to do with the relationship between space and time, or space-time, in which time is a geometric dimension like length, height, and depth. I keep saying time is a geometric dimension, but people don't believe me. The combined effect of general and special relativity on GPS satellites orbiting 20,000 kilometers above the Earth and moving at speeds of around 14,000 kilometers per hour is a measly 38 microseconds, or 38 millionths of a second per day. This may not seem like much, but when these 38 microseconds are multiplied by the speed of light, we find that the GPS satellites would be off by over 11 kilometers per day, or 0.00038 seconds multiplied by 299,972 kilometers per second, equaling 11.39 kilometers. 250 years later, millions of people rely on the physical relationship between space and time that cracked the puzzle of longitude in order to navigate their day-to-day lives. Watch this amazing video produced by the Premier Institute to learn more about the connections between relativity and the GPS in your phone. Oh, it's unlisted.
Perimeter Institute for Theoretical Physics.
Hey, it's Canada.
Perimeter Inspirations. Classroom videos that investigate the frontiers of science. Join host and physicist Damien Pope of Perimeter's outreach team. And
this is from 7 years ago.
Leading scientists as they take you on an educational journey of wonder and discovery.
It's a navigational tool used by millions of people every day. With it, drivers know where they're going. Pilots fly planes more safely. It helps construction workers build straighter roads. Farmers plant fields more efficiently. Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS.
I feel like I'm watching fucking Micro Machines.
So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can.
Sorry, you might not have been able to see this guy's name.
A field and you wanted to
Cliff McMaster University, theoretical physics.
Triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object.
I don't know how much you guys know about like Canadian universities, but McMaster is one of the biggest universities in Canada.
And another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all 3 dimensions, not only where in the field, but how high, and also it's measuring time. You have 4 satellites, they're sending you signals, and you're measuring accurately where the satellite appears to be and when the signals were sent. And from that, you can figure out
Oh, it's a bunch of Venn diagram bubbles.
where you are on the Earth's surface.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals.
I wonder how much math that took to make sure all of the satellites were synchronized in a way that there would always be 4 of them visible at any given point in time. That's neat.
Easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal traveled.
Hey, that's that equation that I said I remembered from like grade 10 fucking science class.
The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters.
To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created.
The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our...
Nobody tell the flurfs that GPS uses fucking the theory of relativity. Their brain will explode.
understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers.
So that means, like, wherever you are on Earth, if you knew where to look and had the tool to do so, you should be able to find these satellites. There should always be 4 of them in the sky at any given point in time.
At a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his
Theoretical physics.
theory of general relativity, which is not only a theory of space-time, but it's a gravitational theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds faster.
So that's how we get the
day.
38.
This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
The effects of relativity on Earth are normally 1 part in 10 billion, and so that's an incredibly small effect, and you're used to thinking you can forget it for most things. But when you're relying on how far light travels in a particular amount of time, if you're wrong by even microseconds, then the distances that you're getting wrong are that much larger.
It's a compounding
To correct
problem.
this error, engineers adjusted the atomic clocks inside the satellites, so on Earth, they ran slow by 38 microseconds per day. This compensated for the effects of relativity and meant that, once in orbit, the clocks ran accurately, giving us the powerful tool we have today.
That's pretty fucking crazy.
So, as you see, What began as an abstract theory over 100 years ago is now used in everyday technology. Every time you use GPS, you're using relativity. Whether you're heading out to meet friends, trying to find the nearest movie theater, or looking for a restaurant in another country, you'll always know where to go using GPS.
So relativity is not just something to study in school. It actually affects daily events in people's lives. Your life.
It's very amazing that after they were developed, they became such an important factor in designing GPSs.
Also theoretical physics.
And navigation systems, and basically we would have been able to do them if we didn't know much about relativity.
On the one hand, you might think of Einstein's theory of general relativity, this theory that space and time are warped, you live in
I could definitely read everything that was on this chalkboard. I definitely know what all of that says. We're good. We're Gucci.
that space and time are warped.
Yeah, you noticed her hair too? She's adorable.
You live in a four-dimensional space-time, you know. You might think that that's the part of physics that's furthest away from day-to-day life, and yet it shows up in this fundamental way in GPS technology, which is crucial to everyone's day-to-day life at this point.
Theoretical physics, closer than you think.
Okay, that's going to be the credits, so I'm just going to let that play. It does say interested in other free educational resources for teachers. There's a website, so I'm going to go to the website and see if we can check that out, see what it says. No, it's blocked. All right, well, that didn't work. But let's look at, I kind of want to look at their YouTube channel, because I'm kind of curious. I'm just a little bit curious. I'm just a little bit nosy, you know what I mean? I don't know about you guys. You guys nosy? I'm nosy. I want to know what's going on. I don't like not knowing. I don't like not knowing when there's something going on. See if there's a post-credits teaser. Okay, we'll wait. I mean, I kind of like leaving the credits on when I can because, you know, props to people doing real work out there. Ugh. I gotta stretch. I'm glad I started these earlier. It's a shame we started a little bit late today because YouTube was running like a goddamn fucking potato. A complete it took me nearly 30 minutes to fucking just get YouTube to load properly for me in my YouTube studio. All right, so let's check out their YouTube channel. Be an explorer. The future starts with physics. World-leading center for theoretical physics dedicated to unraveling the deepest mysteries of the universe. Through groundbreaking research, innovative training programs, and inspiring outreach initiatives, we bring together brilliant minds from around the globe to explore space, time, matter, and beyond. Founded with the vision of fostering collaboration and pushing the boundaries of human knowledge. That sounds like such a Canadian thing to say. Okay, well, let's check this and see if this works. Oh, yeah, that works. So, yeah, if you're interested, this is like down the road. I can go here. I can like walk to this place. I'd take a wander down and check them out. But yeah, that works. I'm gonna see their videos. I want to know when the last video came out. 2 weeks ago. Yeah, so their shit is like up to date. They're still working on this. They 2 weeks ago live. So yeah, if you're interested in physics and want to learn more about physics and stuff, hey, I'm pretty sure that was the guy in the video we just watched. That's crazy. That's pretty cool. Yeah, so if you want to find that shit, go ahead. But we're going to read the footnotes, which is only 2, which is nice. In 2007, the U.S. Navy phased out... Oh, sorry, 1 second. In 2007, the U.S. Navy phased out its celestial navigation program with the ease of high precision and high precision of GPS, it seemed there was no need to go through all the effort to ascertain position at sea. 8 years later, it was back, with the government officials citing cyber threats to technological infrastructure as a concern too big to ignore. Yeah. Good. That's probably a good thing. Like, fucking Christ. For a more in-depth version of this great historical narrative, please refer to Longitude by David Sorbell or Lost at Sea: The Search for Longitude, a documentary from PBS. Okay, well, what is this? Okay, well, that's useless. I'll give you guys the title of the book so you guys can go check out the book if you want, because go to the library. And Lost at Sea, here you go. This looks like it's gonna give me a fucking goddamn virus. Well, that's still available because that's PBS, and that might get shut down in the near future. So, well, it's available. All right, my voice is starting to go and starting to fall apart. I don't know which. We're at Longitude. Oh, we made it 1, 2, 3, 4. We're on the 5th. We already made it to Help I'm Lost, Finding Your Way. And okay, we're like halfway through this already. So good job, everybody. We're making some good progress. I'll be back tomorrow. Same bat time, same bat place with more of this. It is Dumbfuck Friday this Friday, so I will see you guys for that. If you do want me to cover, or me and Manya to look at anything on Friday for Dumbfuck Friday, put it in the Discord. There's a room for dumbfuck shit. So if you want that out there, go ahead. And oh, if you are in the Discord regularly, don't worry about posting something in Educational Political and in Dumbfuck Friday if you want it covered. So just like if you need to post it in 2 places, go ahead. That doesn't harm me in any way. And if you are wanting to share stuff with people, just use the all chat. It's shitpost. Oh, sorry, poop posting. So you can just post your stuff in there and share. And if you're doing artwork and stuff, there's an art share place. So like, don't worry about sharing you and your friends' stuff around, because like we're all about sharing is caring in this wacky world out there. I need to go stretch, go do my workout, and take a nap. Eat some real food. I mean, an apple's a real food, right? Apple's a real food. That counts. I ate a good thing. I gotta figure out what the hell I'm gonna eat. Oh, right, I was gonna make soup. I guess I can start the soup and then it'll be ready because I'm gonna slow cook it. Alright. Thanks, everybody. I'm gonna get out of here. Have a good day, and I will see you tomorrow. Bye-bye.